Okay, so it's time, it's 4 o'clock at my place. So good morning, good afternoon, and good evening, everybody. I'm Gilles Bellet, one of the Organizing Committee chairs, and welcome to IPPW 2021 sixth and last session dedicated to future missions. A lot of exciting presentation today. I wanted to go over some rules and some information before I hand it over to the session chairs. First, all the content that will be presented today is getting archived and will also be available on the International Planetary Probe Workshop YouTube channel within a week. If you go there, you will already see the session 1 to 5 and the posters of this session. Secondly, the meeting itself is also being recorded and be available at the previous mentioned platforms. Finally, please do not unmute yourself during the webinar. All questions must be addressed through the chat box. We will be moderating the mics and kick any person that insists too much on making themselves audible. And with all of that, have a great session, everybody. And now I will hand it over to Pat and Robert.
Thank you very much indeed. So you're all going to be enjoying this session. I'm sure it's, I don't know about you guys, but watching all the IPPW talks this year have been really very good. I think that what the organizing committee did and the program committee did to arrange these sessions in over several weeks was a really good idea, and I think that's really worked quite well. So I hope you've attended most of the IPPW, but I want to welcome you on behalf of myself and Robert. Ashley and Jim Cutts are also co-coordinators, but they happen to be both on vacation this week. So you've got Robert and myself. So today, without much more ado, except to say thank you to Tim and Gilles. Tim Bryce will be running the view charts, and Gilles has been instrumental in getting this organized along with Tim. So let's go on with the session. And our first speaker is Günther Hasinger. Professor Hasinger is the Director of Science and Head of ESAC near Madrid. Over the years, he's had a prolific career at several institutions, both in Europe as well as the US, where he spent several years as director of the Institute for Astronomy in Hawaii. And he has received numerous awards for his research and scientific achievements, including the most significant research prize in Germany, the Leibniz Prize, and the COSPAR Award for his outstanding contributions to space science. He is a member of the Academia Europaea, the Berlin Brandenburg Academy of Science, and Leopoldina, the German National Academy of Sciences. And he's also an external member of the Austrian Academy of Sciences. So please welcome Professor Hasinger. Let's see, you need to be unmuted if you're not.
Yes, excuse me. Patricia, thank you very much for this wonderful introduction. And also thank you to the organizers for the very honorable invitation to give you this update on the ESA science program looking towards the future. So if I could have the first slide, please. This shows the whole fleet of the scientific program of ESA, which is distributed among the solar system explorers, where our topic is today, and the cosmic observers that are looking outward into the universe. And in each of these slides, you see 3 rows. One is the legacy row, where we are standing on the shoulders of giants. And the middle row is the one where we are currently operating spacecraft in orbit. And the top row is the one which we are constructing and are launching in the next few years. Total mission is 14 missions in orbit, 16 in preparation, 22 in a legacy phase. So it's a really very a large body of knowledge that we are kind of organizing. So the next slide shows the zoom in into the solar system. And there I would like to in particular focus on the future, where we are launching JUICE next year. And then we have just selected the Venus mission Envision, and also I would like to show you what is up for the from the just the Voyage 2050 strategic program release, because I believe this also has a very important connection to the decadal service on your side and the cooperation between the two sides is really excellent. So next slide, please. I would like to start with Bepi Colombo. And one of the reasons also to put this up here is that, as you will see, Bepi Colombo is currently, as we speak, flying by Venus. And so this is a very special moment. If you click once more, you see the beautiful messenger results from Mercury. Mercury is still a mysterious planet with several really questions that are still unanswered. And Bepi Colombo is on its way to Mercury, but it takes 7 years to get there. It's 9 billion kilometers and a total of 9 planetary flybys. And we have already done 3 of them now. Next slide, please. That shows the flybys of Bepi Colombo both in April on the Earth on the upper left, and then on the lower left you see the flybys of Venus. We have little video cameras on board Bepi to monitor the health of the spacecraft, and they catch also glimpses of the flying by of the planets. Bepi Colombo is done together with JAXA, where one satellite is from JAXA, the other one is from ESA, and so we are really looking forward when this mission arrives at around the Mercury system. Next slide, please. Then we have launched Solar Orbiter in February last year. This was just before the COVID crisis started, and so we were really very lucky that we could all travel to Florida. NASA launched the spacecraft for us, and there's a very strong cooperation, as you see, between NASA and ESA. And Solar Orbiter surprised us. The next slide, please, which is a little movie. I believe it starts automatically, yes. Solar Orbiter surprised us with these very, very first observations, where very unexpectedly we discovered these so-called campfires on the sun. These are very little. I mean, in reality, they are huge. On the lower left, you see the size of the Earth on the solar surface. So they are covering whole continents on the Earth, but they are still relatively small compared to the overall sun. And it looks like they may be actually important in heating the solar corona and in driving the solar wind during quiescent times. I mean, the sun is not always outbursting and having coronal ejections, but the solar wind is still blowing, and I think the campfires have a very important role in that. Now, Solar Orbiter also, in the next slide, is flying by planets. In particular, is flying by Venus regularly in order to increase the inclination of the orbit, so that Solar Orbiter could actually look from the top of the ecliptic onto the poles of the sun. And so indeed, what you see here in this picture was the flyby to Venus that happened in November last year. But yesterday, Solar Orbiter flew by Venus again. And this is a kind of historic moment because within just a very short period of time, 2 ESA missions flew by Venus. And there's a third mission from JAXA, which is flying around Venus. So there were 3 spacecrafts measuring Venus at the same time. And this is foreshadowing what will actually happen in the near future. Next slide, please. So today and yesterday, we have this closest approach, both of Solar Orbiter and of Bepi Colombo. Both spacecrafts are using the planets in order to decelerate. On one hand, Bepi Colombo needs to decelerate to break angular momentum in order to get in towards the inner solar system. In the case of Solar Orbiter, we are using Venus, as I said, in order to elevate the orbit. But the planets are hugely useful for this billiard game. And if you click once more, then you see we are here, but this was actually when I prepared the slides. In the meantime, the orbits have slightly shifted, and we are already through the closest approach. And so we are actually very much looking forward to see the next pictures coming down in the next, probably tomorrow or so, in the next few hours. Next slide, please. So now, Juice. Yes. So JUICE is actually our mission going to Jupiter, to the Jupiter system, and in particular to explore the icy moons of Jupiter. This shows a sequence with high-speed sequence where JUICE went through the last phases of integration in Friedrichshafen at the Airbus facility. And you see that it is fully or almost fully integrated. And it is basically checked for the last time before it is packed into the container to be shipped to ESTEC. And if you click once more, the next slide is showing how JUICE has actually been tested in the large solar simulator in ESTEC. And that has happened the last few weeks. The whole JUICE spacecraft was integrated in this huge chamber and then was undergoing the full space exposure, both vacuum, cold and hot phases and so on. And so it was very successful. This version of JUICE does not yet contain all the final instruments. There are still 4 instruments missing, the sensor heads. 2 of them have been now successfully delivered. And so we are hanging on our fingernails for the last few instruments to be delivered so that JUICE can indeed be launched in September 22, which would bring us to Jupiter around 2030. So this is really a very exciting possibility. Next slide, please. Now, one of my favorites, I have to say, are these fascinating comets that have actually been discovered entering the solar system from a different system. This object is very well known, Oumuamua, not only because it has such a fancy shape, it's a very elongated, flat body, and it has actually kind of initiated some severe discussion about whether it could be a spacecraft from an alien civilization, because it has been found to accelerate away from the sun. So it flew out from the solar system faster than it came in, and that created a certain amount of excitement. However, this view graph shows a very nice interpretation of our findings, where Oumuamua could actually be a block of nitrogen ice, which has been ejected from an exo-Pluto-like planet. So as we know, Pluto is made up a large fraction of nitrogen ice. And if you have an asteroid impact onto Pluto, for instance, you could chip off a little bit of that nitrogen ice. And then this is traveling through space for a long time. And while it is traveling through space, it is actually weathered and it is getting thinner and thinner. And when it entered the solar system, it was already much flatter than when it was ejected from its own host system. Then the nitrogen ice is actually evaporating because of the warmth of the heat of the sun. And that evaporation is creating an acceleration, a push away from the solar system. And on its way out, when we have measured it, when we have observed it, it was already a flatness ratio of about 6:1. And when it leaves the solar system in about 20 years from now, it will almost have lost most of its mass. So this would be a very nice interpretation of one of the interstellar visitors. The second interstellar visitors turned out to be a normal comet, but one of the comets, actually the comet that was most pristine and most, so to speak, original. And the next slide shows that ESA was actually able to react to these new discoveries in a very fast and efficient manner. We have created an additional mission, which we call Flexi mission, which was actually based on a call for proposals, and this concept won, namely to fly a spacecraft to the L1 or to the L2 system, or to the L2 point around the Earth-Sun system, and then to wait there until one of these dynamically young comets are discovered, either a comet out of our own solar system that has never visited the sun before, or if we are lucky, an interstellar visitor. And so this mission, Comet Interceptor, will actually fly with the ESA M4 mission Ariel, with an exoplanet mission. And so we are very excited. 28 is the launch date for Comet Interceptor, and then hopefully we will discover the right comet to fly to in time. Next slide, please. Then we were very happy to be able to select the next medium-sized mission, Envision. So you know that ESA has the large missions like JUICE, Athena, and LISA. The medium-sized missions are basically things like Euclid and Ariel and Plato. And the next mission is actually going to Venus. It's a very powerful mission that contains, as you will see, several different instruments. And we were very surprised on one hand, but also very happy that almost simultaneously NASA announced the selection of the two discovery missions, Veritas and Da Vinci Plus. And actually these missions were already kind of talking to each other before. So it was already, the Envision selection already took into account the possibility that there will be Da Vinci or Veritas, but that both of them have been selected was a major feat. And just recently we talked with the Indian Space Agency because India is also flying a probe to Venus in the next few years. And so what we are planning is to create a global research program around Venus. So what we call, we are rocking Venus in the next decade. And if you just look at the next slide, you will see a little bit more detail, the fact that Veritas and Envision are actually complementary to each other. Veritas will mainly measure the whole surface from the global, from the whole Venus down to about 10-meter accuracy in certain areas. With a radar system, it will also measure core and mantle properties, but it will do that on a global scale. If you click once more, then on the same representation, you see what Envision will add to there. Envision will be able to measure surface changes, in particular focusing on the so-called tesserae, which is maybe the previous continents, and it will in particular be able to see whether there is lava flows, volcanic activity, or even tectonic motion on the surface of Venus. But then Envision will also have a subsurface radar and will be able to measure the layers below the surface, about 1 kilometer. And it will have several spectrometers that will be able to measure the molecules in the Venus atmosphere. So together, Envision and Veritas will provide a very synergistic picture. And then finally, Da Vinci will land. It will basically go into the atmosphere of Venus and then land on a certain spot. And it will give us ground truth, so to speak, of the global and the more local measurements. And so we are really looking forward to a very exciting decade of Venus research. Now, the next slide. And that brings me to the future. You know that unlike the decadal service on the National Academy of Sciences in the US, which is covering 10 years, the ESA strategic planning cycles are longer. So our strategic planning cycles are covering about 25 years. And in these 25 years, we are typically able to do 3 or sometimes 4 large missions, depending on the budget. And then on the order of 5, 6, 7 medium-sized missions. And when we have actually, right now we are in the middle of the Cosmic Vision strategic plan. That was actually laid out around 2005 or so. And now we are in the middle of that plan. And so it is clear that we also have to start planning for the next strategic cycle, which will then come after these large missions, LISA and Athena, have been launched at the end of this decade. Then we are basically planning for things that happen until 2050. And this Voyage 2050 exercise is actually a completely community-driven bottom-up process. We have selected a senior committee that is sifting through the proposals and looking at the ranking and so on. But then we have asked the community to provide white papers similar to the decadal surveys. And we also have asked the community to self-appoint or self-apply for the committees that are looking at these white papers. So we selected about 50 relatively, diverse scientists from different backgrounds, different age groups, and so on. And these scientists were then together discussing the proposals from the community and then came up with a ranking for the 3 important science topics connected to the large missions in the future. And I'm very happy that they selected a topic, the icy moons of the giant planets, which is basically following up on the fascinating discoveries around Jupiter and Saturn that Galileo and Cassini-Huygens have done, and that will be continued with JUICE. And this theme is really extremely rich, as I will show you in a minute. The next topic was around stars and planets in the Milky Way, either a temperate exoplanet mission trying to do a real spectroscopy in the mid-infrared of temperate exoplanets, or looking at the Milky Way with high precision near-infrared astrometry, following up on the extremely exciting Gaia mission. So in this theme, we are still not fully clear what the technological and implementation boundary conditions will finally be. So this will still be studied for a while. And then the third theme is some new exciting probes about fundamental physics in the early universe. Either a follow-up of the gravitational wave mission LISA, or a very high precision cosmic microwave background spectroscopy and polarization mission. The committee also looked at the technology that are necessary for the future, and they have in particular identified cold atom interferometry, and then X-ray interferometry, new power sources, and then in particular also cryogenic sample return and solar sails. And so these last 2 topics, or the last 3 topics, are extremely important for the topic of this workshop, for the future probes in the solar system. If I can have the next slide, please. Clearly the next mission after LISA and Athena will be another icy moon mission. And you know that JUICE is going to the Jupiter system and will study in particular Enceladus to great detail. And we will actually have to select the next large mission before JUICE even arrived in the Jupiter system. So it's a little bit delicate. But on the other hand, for instance, Ganymede, take it back. JUICE will study Ganymede in the great detail, not Enceladus. But Enceladus in the Saturn system is also an extremely interesting world where Cassini-Huygens have discovered these geysers, these possible cryovolcanism, where subsurface water below the ice layers is actually coming out through cracks, and that water might carry important knowledge about possible biological phenomena, even maybe extant or existing life underground. And so the icy moon of the giant planets theme is clearly focused on this type of habitability, astrobiology studies. And the next slide shows that while this is probably beyond the scope of what we can do currently with our own science program, we are actually dreaming big, and as a part of the so-called Agenda 25 that our new Director General has put out, which is looking for a major increase in the volume of space activities in Europe, we are also dreaming big. And one of the dreams that we have is actually to land on one of these icy moons and to maybe have a cryogenic sample return where we are bringing some material back from one of these icy moons. And this is a place where this is probably too big a mission that we can afford ourselves, but we could at least push the technology in this direction. We believe that we also can do a big jump in cold atom quantum gravimetry, which is necessary for climate observations on Earth, but which could also be used for exploring the icy moons. And so ideally, maybe before 2050, we would like to bring an ice core back. And I believe with this, I would like to end. The last slide, I believe, is just a thank you very much for your attention. And I'm very much available and happy for discussing further with you.
Thank you very much, Gunther. That was terrific. I hope the international collaborations continue, because I think that's a really important thing. So let's see, I'm looking in the chat to see if there's any questions for Gunther. Please take a moment and put things in the chat.
Yes, indeed. I think the international collaboration is really one of the backbones of our work. We are doing so well, for instance, with Hubble and James Webb. We have done great with Cassini-Huygens, and we are really looking forward to more of this big time collaborations.
Yes, you mentioned that the Japanese were interested in the future missions to Venus too. And I think, do you know what the Japanese are planning on that, or have they talked about?
No, sorry, I talked about the Indians. I believe the Indian Space.
Correct.
Yes, so Indian Space Agency is planning a mission to be launched in 2025, 2026. Which is following up on the very successful Moon project. And so they will arrive at Venus first, and then Veritas and Da Vinci will be there, and then Envision will come. So we'll have 4, and then there is already a Japanese orbiter around Venus. So we will have 5 missions from 4 different space agencies.
Definitely the decade of Venus.
Venus.
So question, yes. So question from Gilles is, I love the idea of the international collaboration. Is there a global roadmap in place?
Yes, you see, this is quite difficult because the planning cycles are different between ESA and NASA. ESA has a much smaller budget than NASA, but I think our advantage is that we have a very stable budget, so we can plan over a very long horizon without fearing that at some point the budget will not be there. So we can, in principle, we can kind of put out light posts and say, this is where we want to go to. And that will enable the international community to kind of maneuver around this, either joining or selecting topics which are not directly overlapping. So we are already seeing this, for instance, with, on one hand, James Webb, where we are a minor partner. But then with LISA and Athena, NASA is a minor partner. And so although it is not a formal planning process, it's a kind of adiabatic process that is then still leading to a very good collaborative place. Now more and more actors are coming on the scene, and so we have to see how we can do that. But ESA is actually in an advantage because we can, in principle, and are collaborating with all spacefaring nations. We also have collaborations with Chinese, with Japan. We are just talking to the Indians, to the Saudis, and so on. So we can hopefully foster some kind of dialogue in a more and more complex political environment.
Yeah, I think oftentimes the work that we do in space is actually brings together the international community, which I think is wonderful. So we have a question from Andrew Ball. What's the perspective for technology development for the icy moons?
So the technology development that we are looking for, as I said, on one hand is cold atom interferometers, which are indeed necessary for the next step of global mapping of the Earth. There is an Earth climate mission. If we could have cold atom interferometers, we could basically measure flood waters and all kinds of effects of climate change, not just the change, but also the mitigation. And if these sensors are developed, then we could also try to employ them in the planetary world. So ideally, we would like to fly a cold atom interferometer sensor to one of the icy moons to, for instance, localize where the weak spots in the surface are, where the water is coming out. And then indeed, either if we are not able to land, then I believe one interesting technology would be to fly through some of these geysers and try to collect the material while you fly. But the dream would really be to land and to bring back a cryogenic sample. So, I mean, the temperature is minus 200 degrees there roughly, and you would like to maintain the temperatures on the way back to Earth in order to bring the sample more or less in the frozen form, because otherwise you will lose more or less the context and the information about the history of the sample.
Yeah, that's a tough job. We've looked at that for some years. It's a tough job. So there's another question here from Gilles. How do you see the place of CubeSats, both standalone and rideshare, in Voyage 2050?
You know, the Voyage 2050, the main exercise was to identify the three big themes, the three big topics, which are flagship missions in a sense. And then we have identified a number of possible themes for medium-sized missions, for M-class missions, but they are not prescriptive. So they are not a selection, they are just a kind of menu from which people can choose. But then the smaller elements we have not really kind of prescribed, because we are hoping that we can do more of these F mission fast and flexi missions that I have explained in the case of the Comet Interceptor. So we are already now planning 2 more fast missions, depending on how the budget the negotiations will go, but at least 1, hopefully 2 fast missions. And those fast missions could in principle be a small satellite. So like Comet Interceptor is also not just 1 spacecraft, but it is actually one mothership and 2 small satellites which are kicked out. And so you could imagine a whole slew of maybe a constellation of small satellites as an F mission. And indeed, there are some discussions to fly CubeSats around the moon. This is our Chinese colleagues are planning to have low frequency radio telescope flying around the moon. So this is clearly in the air, but we don't really prescribe it, because the science program is more or less completely bottom up. So the community needs to react to the possibilities in our budget.
Yeah, I know there's some really innovative things I think is happening in Europe. I know there's a technology demonstration OPSAT that you guys have that are really good. You just test out your technologies in these CubeSats. It's a terrific program, I think.
And indeed, I think it's a little bit because the science program that I'm representing is only a fraction of the whole ESA program. But ESA also has technology missions. For instance, there is Proba 3. It will be 2 CubeSats which are flying information, and they are actually doing high resolution measurements, coronographic measurements of the sun. So in other contexts than the science program, there are indeed the CubeSats are playing an important role. We are just trying to give a kind of baseline, a platform on which the scientists then can use these technologies and employ them in the future.
Yeah, that's great. So thank you very much indeed, Gunther. I think there's time to get on to our next speaker. And I appreciate all of the information that we've gotten from you. That's just fabulous programs that we're looking towards.
Excellent. Thank you very much.
Thank you. So our next speaker is Sarah Seeger. Sarah is a professor of planetary science, physics, aeronautics, and astronautics at MIT. She works on space missions for planetary discovery and exploration, and was the deputy science director of the MIT-led NASA mission TESS, which is currently on orbit, and PI of JPL MIT CubeSat Asteria, which I worked on with Lorraine. So this has been a really useful mission that we've done a lot of work with. Sarah's current research interests are focused upon exoplanet atmospheres, interiors, and signs of life by way of exoplanet atmospheric biosignature gases. And today she'll talk about Venus Life Finder mission concept study. Sarah?
Thank you. Thanks, everyone. Can you hear me okay?
Yeah, we can.
And can you hit next for a moment, because it's not showing up some of the credits that were supposed to be on this cover slide. This is the wrong talk. I'm sorry. This is not what I meant to show. I was wondering if you'll let me try to share my screen. I'm not sure how that happened.
Sure. I think we can give you the ball. Let's have a look here.
I really appreciate it.
Yeah, hang on. Tim, can you hand the ball to Sarah?
Tim, I'll do it.
It's definitely, yeah, I sent him the wrong talk by mistake. I apologize for that.
Okay. Thank you, Beth.
You are now a presenter. You should be able to share your presentation.
Can you all see this?
Yep, if you go to presentation mode, that's good.
Yes, I'm in presentation mode. Can you see presentation mode?
Now we can. Thank you so much.
Okay, thank you. I'll get started. Hi, everyone. I'm Sarah Sager from MIT. Thank you for the introduction. I'm here to give you a status update on the Venus Life Finder mission concept study. We are a small group of scientists and engineers and industry partners, and we're sponsored by the Breakthrough Initiatives. This is just a study right now, just to sort of clarify, we don't have funding for an actual mission. And we are a astrobiology focused mission. We're thrilled about all the interest in Venus, the new selected missions, and we aim to be complementary. For example, none of the selected missions will have an in situ probe that interrogates the particles, the cloud particles in the Venus atmosphere. So just to make sure we're all on the same page, Venus is on the surface literally appears to be the worst possible place for life because the surface, due to the massive carbon dioxide greenhouse atmosphere, is too hot for life of any kind. Nonetheless, since Carl Sagan over half a century ago, people have speculated about life in the clouds. The surface at around 50 kilometers, the temperature is fine for life. Moreover, there's a liquid environment and all life needs liquid. Yet even in the clouds, Venus is nearly impossible. It's nearly impossible for us to imagine life surviving because of the extreme cloud layer humidity is lower. It's more dry than the driest place on Earth. And the droplets are concentrated sulfuric acid, which is incredibly acidic, actually orders of magnitude more acidic than what life on Earth can survive in. And so you'd wonder, why are we all considering this? And it's actually partly because of some very intriguing atmosphere anomalies. I don't have time to review it here, so I'm just going to flash this slide up, and there'll be more information later on in papers. But there are three anomalies I'm mostly intrigued with. One is the presence of molecular oxygen as measured by different in situ probes from the 70s and 80s. The possible presence of ammonia measured by a Venera probe as well as Venus. And what's well known in the community that the vertical profiles of sulfur dioxide and water vapor are not explainable without modeled artificial fixes. There's a major depletion of sulfur dioxide in the clouds. And Paul Rimmer recently came up with a theory that salts lofted from the surface could get absorbed by the droplets and neutralize them essentially to an acidity of pH -1 to 1, which is still very acidic, but more consistent with extremophiles on Earth. We've taken this, actually, this also naturally explains the depletion of SO2 in the clouds. Now, I can't dwell on it here because it's not what my talk's about, but some of us have come up with an even new theory It may be really too extreme for you folks, but it's just to say that you have to pick your poison. You can artificially modify your models. You can assume this, assume that. But if you assume that there's life in the clouds, making ammonia, you actually can solve a lot of these issues. And more on that another time. I just put this here to tell you that we're incredibly motivated to remeasure the anomalies, to determine the acidity of the cloud droplets. We want to know how dry the atmosphere is as well, and understand the cloud particles a little better. So we have 3 missions, small, medium, and large, that we have been studying. We have teamed up with Rocket Lab to be their science team and to guide the choice of science instruments. Now you'll hear more later from the Rocket Lab team later today in the session. I've actually picked out the three things that, as just like scientists, we care about most. Launch planned for May 2023. It's a really small mission. So the whole probe would be like, a probe would be dropped into the Venus atmosphere. It would be 15 to 20 kilograms with up to 3 to 4 kilograms or less for the science instruments. That's tiny. And this probe would just go down in the atmosphere without any way to slow down, 3 minutes in the cloud layers. Again, our goals for all of our missions are to search for evidence of life in the clouds. We have 2 objectives for our mission. One of them is to detect the presence of organic material within the cloud layer particles. Admittedly, this isn't proof of life, but it would be very, very compelling, intriguing to find signs of organics. The goal would be to autofluoresce particles, shine a laser out to the cloud particles and see if any of the material fluoresces. On Earth, many organic compounds are known to fluoresce when subject to ultraviolet light. There's some examples at the bottom here, including wavelengths of UV that fluoresces them. We're still working to choose the one UV wavelength that might be the best one for us to take on this first mission. Our second objective is to look at the gases for signs of disequilibrium chemistry. We're very, very interested in ammonia gas. That is our #1 gas we're interested in. Water vapor, as I mentioned as well, and our instrument that I'll get to in a moment can also can detect water vapor, and it can also detect D to H ratio as well as O18 to O16 ratio. Because we could only choose 2 gases, we've left out one of our, let's call it favorite molecules, phosphine, very controversial, of course, but might be patchy, and we don't want to come home empty-handed. We have to leave off methane, another reduced gas, because it's an ablation product from the heat shield. And oxygen, we also want to reconfirm its presence and measure the values. Our instrument would not be sensitive enough. So this is going to go quickly, but the talk and the slides will be available for you to read later. And at some point when we're finished our report, we'll make that public as well. So our first instrument is a really small instrument. This is a autofluorescence nephelometer. The nephelometer is based on a commercial product that's attached to the outside of aircraft, and it's made by Droplet Measurement Technologies. Droplet, so it will shine a light to the particles, which will bounce back in a range of angles, and including polarization. And looking at the distribution in the angles can help constrain what the particle is made of and the particle shape. And if the shape isn't spherical, as has been indicated by the Pioneer measurements, that means the particle is not liquid, which is of big interest to us because it helps with the theory that there's salts or there's ammonia creating non-liquid in the particles. So Droplet Technologies and Daryl Baumgartner, the lead, had a brilliant idea that he could use the laser that's going to do the nephelometer part of the instrument could double as the ultraviolet laser that tries to incite fluorescence in the molecules. So this is a combined instrument. And we're really excited about this instrument. We think it will has the chance to not tell us what organics are there, but if organics are there. And this instrument would be less than a kilogram. Our second instrument is the mini tunable laser spectrometer out of JPL. This is a very mature instrument. It's used on the ground commercially. It flies on Earth science balloons. It has been on the SAM Mars Curiosity rover. This is incredibly sensitive. It has limited detection of gases to parts per billion. And this instrument has 2 channels. So again, we'd choose ammonia and water vapor. And here, this instrument weighs 2.3 kilograms. There is a way to the housing actually is about 1 kilogram. So we think that we're hopeful we can squeeze both of these instruments on the Rocket Lab mission. It's all still TBD. So our medium mission, just as an overview, it is a balloon mission. And we tried to come up with the smallest, simplest, although those words are a bit ironic when it comes to balloons, mission we could think of. I wanted to say that last week, there were two great keynote talks by Paul and Colin about the science, and there were also a number of talks of aerobots. So I refer you back to those talks as well. Here, you can just read the slide, but it's just illustrating the entry and the inflation of the balloon. But the key points for you are that our balloon is about 4 meters in diameter. It's about 13 kilograms. And this balloon design is by Maxime de John at Thin Red Line. This balloon would have a gondola. The total gondola mass is about 30 kilograms with about 8 kilograms for instruments. Our balloon would be designed to be a fixed altitude balloon at about 50 kilometers. And we would have 4 mini probes. We drop these down to sample the atmosphere below our balloon. Our balloon would last about a week, maybe a little longer, and it would communicate to Earth through an orbiter. So all that you might have heard of before from other people, but we thought really carefully about what we want to do with this mission. We want, and some of this overlaps with what Colin talked about last week. So we, again, like to know the acidity. We'd like to know the amount of water vapor in the cloud layers. We'd like to measure some of these gases that I talked about. We'd like to know if there are metals in the cloud particles, like iron and other metals, because life needs metals to catalyze biochemical reactions. And finally, we actually are very keen on a future of sample return. So I'm glad the previous speaker from ESA mentioned sample return. We'd like to prepare in this mission for sample return by determining, if some of the cloud particles are solid, because that informs our capture mechanism. We'd like to know the level of homogeneity of the cloud particles. If they're all the same, great, we could mix them all together. But if they're, there's that 1 in a million particle that stands out as different, we have to think more carefully about how we're going to capture things. So again, you can read this table later. These are the instruments we've more or less settled on. And again, this is just a concept study. But what's new here that you might not have heard about or thought about before is a pH sensor. We have motivated 2 different groups to study single particle pH measurement ability, because we want to know if these are concentrated sulfuric acid droplets or if they're indeed something else more suitable for what we think life can handle. We also have a MEMS device. It's called a microspectrometer. It would basically ionize aerosols, and it would, by the recombination emission, would measure visible infrared, like spectra, if you will, to see what metals might be there. This is a tiny, tiny instrument. It's made in Poland, and it has to be tailored for whatever metals you're interested in.
2 minutes, Sarah.
2 minutes. All right. So just to wrap up here, we have our notional concept for atmosphere sample return. Solid surface sample return has been mentioned before for Venus, but here we're only focused on the atmosphere. Our goal would be to bring back 1 kilometer of gas and 1 kilogram of gas and 1 kilogram of cloud particles. We actually thought a lot about bringing along a microscope and a mass spectrometer, and we still have a version of a medium mission that does that, but those were so complex and expensive, and they couldn't really reach the limits of detection that we needed, especially in terms of small size of what might be any signs of life or cells in the atmosphere. So to summarize, the Venus LifeFinder mission concept study, we're an astrobiology focused series of mission concepts, culminating with atmospheric sample return. I'd like to thank the core team, the extended team. A lot of people in this audience have contributed at our community meetings. And I've listed here another thanks to our industry partners. And finally, again, thanks to Breakthrough Initiatives for sponsoring this study. Thank you.
Thanks so much, Sarah. Let's see. This is fascinating. Yeah, it's too bad that Richard's on a plane right now, so he couldn't actually make it until the end of the session, but it would have been really good to hear from him next. However, we'll hear later on about the Rocket Lab side of things. So any questions for Sarah? Sarah, they said the launch was 2023, you said?
The launch is planned for 2023, correct.
Yeah. So that's pretty ambitious. Have they started?
Yes, you can, like the good thing is since Richard will be here, you can direct those questions to Richard. So yes.
So Stephanie Getty asks, Sarah, thanks for the presentation. Is your small mission a direct entry architecture?
Yes, it is. So a cruise vehicle will drop off a small probe that will enter the atmosphere directly, and it will communicate with the cruise vehicle, which will just be flying by Venus. That will act as the communications relay back to Earth.
Okay, so we're going to have to move on. Thank you very much indeed. Sarah, could you send us your corrected presentation?
Yes, thank you.
Yeah, thanks so very much. Okay, our next talk is by Samuel Frampton from the University of Leicester. Samuel is a PhD researcher at the University of Leicester. His research interests include the use of new space techniques for planetary science missions, including concept studies, interplanetary trajectory design, and communication architectures. And today he'll talk about multi-probe icy moon mission.
Thank you. Can everyone hear me?
Yep.
Perfect, thanks. Thank you very much for the opportunity to speak. Those are some pretty tough acts to follow, but I'll do what I can. So yes, I would like to present our concept study on a multiple probe icy moon mission. This has been a collaboration between researchers here at the University of Leicester, as well as members at DLR Berlin, Aachen University, University of Dayton, and Politecnico di Torino. So if I could have the next slide, please. So just to set the scene a little bit, as I'm sure you're all aware, current plan is for Europa Clipper to launch in 2024 and arrive in 2030. It will be the first mission dedicated to Europa with a clear focus on trying to determine how habitable the moon is. But it is an orbiting mission, and it seems that the next logical step, depending on the data that's returned from Clipper, will be for a lander. There have been several lander concepts studied, including Europa Lander itself, but there isn't currently a clear roadmap on what the next step post-Clipper will be. And it does seem fairly apparent that any habitable zones are likely to be in the subsurface ocean, so below the surface ice. So there is a need to figure out how we're going to get through that crust and into the subsurface ocean. In terms of how we've been looking at it, we kind of see that there are two major challenges to this approach. The first is actually getting through the ice itself, and the second is how do you transmit that data back from the subsurface ocean through the ice. And we're hoping that some of the space nuclear power technology developed here at Leicester could help address those two issues. Next slide, please. So I'd like to introduce our concept for a multi-melt probe concept. On the right there is a quick illustration of how we see this concept playing out. So there will be one main scientific probe, which will include all the instruments necessary to assess both the ice and the subsurface ocean. And with that main scientific probe, there will be several smaller communication relay probes. The smaller probes would be very simple. They would only contain the nuclear power source and the communication architecture required to transmit data back to the surface. And we would ensure that these probes melt through the ice at a slower rate than the scientific probe, so that you would reach a point in the third panel there, the subglacial analysis, where the communication probes are distributed throughout the ice so that you can create a positive comms relay. The scientific probe would collect data. Eventually, they would drift apart further, at which point your mission would be at an end, as you wouldn't be able to transmit data back to the surface. In terms of the environment we'll be working with, estimates of the ice at the surface of Europa range from about 40 kilometers to, as Gunther mentioned, on some regions, there are very thin regions of ice up to a couple of kilometers at localized sites. And also the salinity has quite a wide range, ranging from about 5 to 45 kilograms per meter cubed above pure water ice. So until we get some data back from Clipper, we have some variability in the components of the Europa ice, which pose quite a significant design challenge. Next slide, please. So yes, just to go into that a little bit more detail, we hope to leverage some of the radioisotope work that has been done here at the University of Leicester. On the right there, you can see some of the radioisotope thermoelectric generators that we are currently developing. We'll be looking at launching post-Clipper once we have some more information on the European environment. And our current work, as I mentioned at the beginning, is focusing on the communication chain, trying to establish that positive comms margin through the ice, and also how the probes themselves will not through the ice. Next slide. So just to go over this quickly, in the top left there is the ratio of the power of an RF signal after a given distance Z through an arbitrary medium. Epsilon there is a dielectric permittivity, which is inherent a characteristic of the medium. And this dielectric permittivity directly affects your attenuation length of an RF signal. So to design the comms link going through any material, you would really have to constrain this value. The imaginary index on the right of those two equations can be written with a direct frequency dependence, and A, B, and C are empirical measurements of the material. And even within terrestrial applications, these measurements can vary quite significantly. So on the graph on the left here, it's two of the average temperature profiles as a function of depth for Europa. These are from our colleagues at DLR Berlin. As you can see, there's an agreement amongst the average models of leveling off of the temperature around 260 Kelvin, about minus 15 degrees C. But the density profiles, the orange being the higher density and the gray being the lower density, affect what depth the plateau is reached and at what rate the temperature drops over those first 10 to 15 kilometers. Next slide, please. So this is a plot of some recent studies on dielectric permittivity. The green bar shows the range of temperature and salinity that we might expect at Europa based on those models again. And the error bars show the range of temperatures and salinities those studies took place. The one at the bottom is from Bryant 02, and that wide temperature range was extrapolated values rather than directly measured, which is why they span all of the European temperature profile. But as we can see, there are several gaps in the measurements for the range of temperature and salinity that we might expect in Europa. So we're therefore proposing an empirical study to be undertaken here at Leicester to investigate some of these RF properties of the ice. Next slide, please. So as I say, we're currently setting up an experiment to investigate this relationship further. We currently have a software-designed radio on the bench with about 1 to 6 gigahertz frequency. We'll likely be using the lower end of this to minimize absorptivity through the ice. So the radio will be controlled through open source new radio software, which we'll use to set up the data stream and the coding and encoding before we fire it through the block. To achieve the temperatures that are required, we currently have a cryocooler in the department, which is able to reach minus 40 without liquid nitrogen and minus 85 with it. Fridge is currently being rewired to get up and running, but we're hoping to get that up and running by the end of this month and starting to get preliminary results by the end of the year. On the right there is a quick diagram from Matzler and Wegmüller in 87, which is the kind of experimental setup we'll be looking at emulating, as this is the experimental setup that was used to extrapolate some of those RF parameters for Europa at high temperatures. Next slide, please. So yes, the descent of the probes through the ice is another key challenge. Multi-probes have been designed and deployed in terrestrial applications, and we're looking at self-contained power and heat elements for the comms and the science probe to melt through the ice. Based on the technology developed at Leicester, and we're hoping that these probes would be able to be completely self-contained as they melt through. Next slide, please. So as I showed in the Europa models, the ice characteristics alter over depth non-linearly. So this affects not only how quickly a probe would melt through the ice for a given heat power, but also it would affect the distance that an RF link could be established. On top of this, the radioisotope sources also excuse me, the radioisotope sources also develop over time. So we're currently looking at a curium-244 fuel, which, as you can see, the power output of will reduce slightly by the time we would be able to reach Europa. If you'd like to learn more about some of the fuel choices, I'd like to direct you to the Ambrosi et al. Paper at the bottom right there. On the left, this is the beginning of some of the modeling that we've been doing for the descent of the probes. This is taking into account the variability of the ice and the evolution of the fuel over the time. Once again, if you'd like to see a bit more about some of the melt modeling work we've been doing, I'd like to direct you to the poster in the box at the bottom there by Boxberg. That was presented at the Innovative Concept workshop of IPPW this year. Next slide, please. So we did some preliminary sizing to make a first run estimate of the communication and the melt modeling, and it's been designed to fit within current deliverable mass ability for Europa. We've been assuming the worst case scenario, so assuming 40 kilometers depth of ice before reaching the ocean. In this scenario, you may need up to 30 of these comms probes to actually reach through. But once we have further data on Europa, it may be the case that we'll be able to select a slightly more reasonable landing site. It may be that 40 kilometers is a bit too conservative, but we're yet to see. As I say, if we are able to choose one of these thinner ice probes, we'd be able to allocate more mass to the instrument suite. The instrument suite is currently quite difficult to select, as we would need more data from Clipper to understand the type of biosignatures that they're looking for. As I've put in mentioned there underneath the table, the T0 refers to the time at which the mission has landed and the probes have been released. So the power output from the radioisotopes has decayed before it's reached the surface. Next slide, please.
2 minutes, Sam.
Okay, perfect. This is my last slide. So yes, just to clarify, on the left there, I've put some of the next steps that we'll be looking at is looking at the RF attenuation measurements. We'll also continue the melt modeling work that we've been doing, and also looking at how sensitive that is to the range of Europa profiles we might expect, and also if we'll be able to profile any of the landing sites. And on the right there are some of the key questions that we're hoping our research might be able to address. So I'm happy to take any questions or comments now. Otherwise, I've put my email at the bottom there. Please feel free to send me an email that won't fit in our allocated time. Thank you very much.
Thank you, Sam. That's great. Thank you. We do have some questions. There's actually a debate going on, so maybe you can weigh into the debate here.
Okay.
Isn't a nuclear energy source an issue for planetary protection, as any surviving organisms on Earth could thrive with this heat source and the surrounding water? And Giles refers to some work at JPL where we talked about where JPL, sorry, my screen jumped. There's too many interactions going on.
Yeah, I don't know if it's a good or a bad thing that I've started a debate in the chat.
Anyway, we've looked at this powered lander and self-cooking at the end of the mission, but would you like to just comment on the planetary protection aspects of this?
Sure. Well, the work that we've developed for the radioisotopes, they have to be, they have to fit with planetary protection for Earth. If there's a failure case in the launcher, we have to make sure that they're self-contained. So they are heavily rated for high impact, and equally, as I showed from some of the fuel development on slide 9, that the fuel source will degrade over time to a point that the heat that it's giving off a decade or so after the mission will be not as much as an issue. But I agree completely that it's a key factor that we need to look at.
Yeah, I think that there's quite a lot in the chat, so maybe you want to weigh in on the chat, and I'll just go to ask a couple of other questions that came up. Can sufficient quantities of the curium-244 be sourced from available production capabilities?
As far as I'm aware, yes. I would direct you to that paper, but we have looked extensively at how we can source this fuel from European sources, and it seems like that quantity is able to be produced with relatively little problem.
And then one last question. Okay.
Oh, yeah, sorry, I was just going to say directly to my colleague's paper.
Okay. And one last quick question. What do you see as the advantages of your architecture versus a single melt probe that detaches parts of itself at prescribed depths to serve as the comm relay links?
Sure. Well, the first is that the control of the probes is passive. So as I say, we're controlling the melting and the velocity that they descend purely from the amount of radioisotope fuel in them. So there's no kind of uncertainty about where you're putting those probes. They will deploy at the given depth based on the mass in them. There's also no issues of anchoring and those kind of moving parts in that architecture. So I think the main advantage is that it's all kind of passively controlled rather than having to pre-program deployments at given depths.
Okay, thanks. And I think we're going to have to move on now.
Okay, thank you.
Pat,
Oops,
I can't hear you.
Oops, I was on mute. My apologies. Thank you.
So you can hear me.
Yeah, I can hear you. Yeah, so let me just introduce you again. Did everybody hear the introduction? No.
No, please repeat.
Okay, so Kerry is at Global Aerospace Corporation. He currently manages the development of Air Force hypersonic aeroelasticity wind tunnel experiments, including test article and sensor design, fabrication, and testing. He also owns a patent on enveloping aerodynamic decelerator, a key technology enabling the Pluto hop, skip, and jump mission that he'll now talk about. Thank you, Kerry. Sorry for my muting.
That's fine. Thank you, Pat. The Pluto hop, skip, and jump mission is a NASA Innovative Advanced Concept, that's NIAC. It's a program phase 2 project, and I'm the principal investigator for that. Next slide, please. So since the New Horizons mission flyby in 2015, Pluto's been considered a very exciting Kuiper Belt object, KBO. Some of the unexpected findings were that Pluto and its moon are very complex, and there's been recent and ongoing activity on the surface. The atmosphere condensation rate is significantly lower than predicted, and that's important for us. And finally, there's evidence of an internal water ocean. So these discoveries have increased the interest in the Pluto system and other KBOs, and instigated studies of their exploration by orbiters and landers. Next slide. Looking at the high priority decadal survey themes of the last survey, under formation, the Pluto system records physical and chemical properties of the Kuiper belt, the solar system, binary systems, and giant impacts. Under habitability, Pluto has complex organic chemistry, abundant in hazes, and measurable tholins, which are organic substances that are affected by UV radiation, and possible subsurface ocean and cryovolcanism. Under workings, we note that the processes on Pluto are diverse, unique, and ongoing. Next slide, please. So the challenge of this mission is slowing down from a very fast interplanetary approach speed and landing on a planet with very little atmosphere, and doing so with a low mass system. For a short flight to Pluto, let's say 11 years, the approach speed is about 14 kilometers per second. That's the same flyby speed as New Horizons had, and about twice as fast as Earth orbit speed. To make matters more challenging, the Pluto atmosphere is only about 1/100,000th of the Earth's surface pressure. So how can we land on a planet given these conditions with a low mass system? So if we meet this challenge, we could do a Pluto lander mission with a budget similar to NASA's New Horizons mission, and we think that's significant. Next chart. The key innovation for this concept is the ultra-low ballistic coefficient decelerator. We call the enveloping aerodynamic decelerator EAD, that enables a very high altitude deceleration, which keeps heating rates 2 orders of magnitude lower than conventional entry capsules. The current near Pluto landing sequence is as follows. We deploy and inflate the decelerator envelope prior to reaching the atmosphere to about 60 pascals, after which we jettison the inflation tanks and the cruise RTG heat exchanger. We enter the atmosphere with a velocity just a little larger than 14 kilometers per second at a reference altitude of 1,600 kilometers. About 2 minutes later, we reach peak heating, which is only about 3 watts per square centimeter. The dynamic pressure is about 36 pascals, but the deceleration is about 30 Gs. We decelerate to a speed of about 120 meters per second, about 700, that's our terminal velocity, about 700 meters above the surface, where we separate the lander from the decelerator, deploy landing legs, and fire thrusters to translate away from the envelope and land gently on the surface, after which we perform science measurements at the initial landing site, but we're able to fire the onboard thrusters to hop around the surface to investigate new sites tens of kilometers away. Next slide. This chart discusses the spacecraft concept, whereby the lander functions as a cruise stage on the way to Pluto. On the upper right is a 900 kilogram interplanetary cruise configuration showing thrusters, RTG radiator, inflation tanks. The radiator, inflation, and cruise propellant tanks and envelope cover are jettisoned prior to entry, and inflation. They're jettisoned prior to entry. On the upper left is the 70-meter diameter inflated EAD with load lines that attach to the payload. Those load lines allow us to transmit the G load of the lander into the equator of the envelope. The lander is shown at the windward end of the envelope, and the entry mass is about 640 kilograms. In the lower left is the 213 kilogram lander, showing about 38 kilograms of science payload, antenna, propellant tanks, structure, and RTG. Next slide. Here we have the reference approach and landing geometry and the V-infinity sun plane. The Earth terminator, your sun terminator, and they're very close to each other, divide the day side and the night side. We want to try to land on the day side if possible. Note there are acceptable landing areas on the far side that eventually rotate to the day Earth side for communications. The nominal flight path angle is about 62 degrees with an entry flight path angle corridor of about plus or minus 2 degrees. The green shaded region on this chart is the acceptable landing sites based on that flight path angle. Atmospheric uncertainty is obviously a concern, which is why we plan to conduct a Monte Carlo analysis in the NIAC Phase 2 to understand the contributions to the key uncertainties to landing uncertainty. Next chart. This is a view of Pluto on the approach at the reference mission arrival time. Note we're approaching from the North Pole, essentially. So this is kind of an upside down view of Pluto, as you might remember or see usually. The light green area near the planet edge shows the landing zone based on the acceptable flight path angles. This zone extends beyond the planet limb around the back. This figure also shows that we can reach several interesting landing sites in the northern hemisphere by adjusting the time of arrival by plus or minus 3 days, which is about half a Pluto day. The yellow X is an example landing site, and the yellow curve is the path the site would take as the Pluto rotates during the day. Next chart. So this chart summarizes a study of a Triton lander on a secondary payload on a Neptune orbiter. Triton, the largest moon of Neptune, is similar in mass, size, surface composition, and atmosphere to Pluto. Triton is a particularly scientific interest because of its retrograde orbit, meaning it might have been captured KBO. NASA's roadmap to ocean worlds identified Triton as the highest priority near-term ocean world target. And during the Voyager 2 encounter, active geysers were seen along with over 100 dark streaks that could likely have been former geyser eruptions. Triton's similarity to Pluto makes it favorable to entry, descent, and landing by our ultra-low ballistic coefficient EAD technology. For an orbit mass of 40 kilograms, a small 20-kilogram lander could be placed on the surface. Larger direct entry landers and orbiters have also been considered. Next chart. So in summary, the proposed science is not just relevant to Pluto, but to all KBOs. A Pluto lander mission is possible in 11 years with a mass comparable to New Horizons, a mass and cost comparable to New Horizons, and just one RTG. Pluto EDL, entry, descent, and landing, using aerodynamic drag is feasible due to the ultra-low density enveloping aerodynamic decelerator technology. A lander mission enables Pluto science on the surface and new atmospheric measurements. Future steps include Phase 2 NIAC work and a proposed Phase 3 NIAC effort, CubeSat flight demonstrations of EAD technology in LEO, and continuing to mature concepts for KBO landers and orbiters under mission design studies. I'd also like to direct you to our poster talk in this session about the key EDL technology, the enveloping aerodynamic decelerator. Final chart. We'd like to acknowledge the NASA NIAC and SBIR programs for the support of the work that's led to this mission concept. Thank you.
Thanks a lot, Kerry. That was great. Let's see, we have some questions. Jeff Landis wants to know, what is the diameter of the EAD balloon?
For this example, the nominal diameter is 70 meters.
Okay, dokes, thank you. And Athol wants to know, what is the ballistic coefficient of the inflatable entry system?
It's about 0.15.
Okay. And Jeff Hall wants to know, how do you separate the balloon from the spacecraft once the deceleration phase is complete?
Well, that's something we have to look at, but I'm thinking that there are zip cords that are available that can easily separate the envelope from the solid surface of the lander, and the envelope is going to be pulled back by the aerodynamic drag as the lander falls towards the surface, and then we translate away from the envelope so we don't get encumbered by it as we land.
Okay, Kerry, thank you so much indeed. And we're going to have to move on to the next talk, which is the last talk before the break. The next talk is by Jarvis Songa. And let's make sure I'm not muted this time. Yes, so Jarvis led aerothermal analysis and thermal protection system design efforts at Lockheed in close collaboration with NASA Ames. His other experience includes related roles on Phoenix, MSL, Insight, and Mars 2020. He has a BS in aerospace engineering from the University of Kansas and MS in aerospace engineering from the University of Colorado Boulder. He's going to give us a talk today about the journey of the OSIRIS-REx sample return capsule. Welcome, Jarvis.
Hello, everyone. Can you hear me fine?
Yeah, we can. Thanks.
Great. Okay. Yeah, we'll be talking today about the OSIRIS-REx mission, specifically with a focus on the sample return capsule. Next slide. So OSIRIS-REx launched in 2016 with the primary objective to visit the near-Earth asteroid Bennu, to survey the asteroid, learn more about it, and then ultimately obtain a sample to bring back to Earth. If you look at the photo on the right, the white object there in the center of the science deck, we're looking at the science deck, that's the SRC, sample return capsule, which is a near build to print of the Stardust capsule. Same geometry, same TPS materials. We have Pika on the heat shield and SLA 561V on the back shell. And it's the only real changes from Stardust are internal to accommodate the tag SAM sampler head. On the lower left here, you can see what OSIRIS looked like when it performed the tag maneuver. So it extends an arm down. At the end of that arm is what we call the tag SAM sampler, touch and go sampling mechanism. That works by injecting gas into the surface to collect sample. And then that arm can rotate up to stow the sample into the SRC. So we had about a 2-year outbound cruise, and then followed by nearly 2 years of looking at Bennu to find a site. On October 20th of last year, we finally actually did touch and go and obtain a sample. And currently OSIRIS-REx is on return cruise, portion of its flight coming back to Earth. If you go to the next slide. So in that outbound cruise phase, we didn't expect much participation by the SRC, really just a passenger on the spacecraft. But we did actually find something that was a surprise to us. One of the things planned in outbound cruise is to test the spacecraft in various orientations, look at the thermal response and the spacecraft behavior in those orientations. The first time we went into the toe dip orientation, we noted, the nav team noted in the Doppler data, pretty significant unmodeled delta V, and we had to go take a look at where that might be coming from. Operations around Bennu requires some pretty precise maneuvering. The delta V we were seeing was on the order, about an order of magnitude above what gravitational forces from Bennu or solar pressure would be in those near Bennu operations. When we reconstructed this, we found this was the first time we'd really put the SRC in the sun for a prolonged amount of time. So it was an immediate candidate for maybe where this delta V was coming from. We know that Pika absorbs water. We know that that's not an issue for entry performance. But here, that was a suspect for what could be causing this delta V. That we had ice in the TPS that then sublimated out as we rotated into the sun. And doing some analysis showed that that was definitely the most likely candidate. We subsequently planned an outgassing campaign during that outbound cruise, putting the SRC into the sun a little bit at a time. Couldn't expose the whole science deck, but we could expose the SRC to some degree repeatedly. The plot on the lower right shows what we saw when we did that, in that as we repeated those exposures, the unmodeled delta V decreased until finally it was down below the measurable noise threshold before we ever arrived at Bennu. Like to credit Scott Sanford for really taking a look at the outgassing products on the ground, because not only was this delta V a concern, if the Pika was outgassing something other than H2O, there was a risk of contamination of the sample. So that was something else that was looked at and determined that only benign products were coming out of the Pika, so no risk to the science. So that's a kind of a perfect example of how the whole system plays together in ways you don't always expect. Go to the next slide. So from the earliest phases of the OREX mission, design phase, what would we find at Bennu? That question was right at the top of the list. We had some really significant uncertainties, especially from the perspective of an engineer, in what we needed to design for. And then as we performed ground tests and better understood what TAGSAM was doing, the question kind of emerged, when we sample on this asteroid, is there a risk to the spacecraft, to the SRC, which is pointed directly down at the tag site? You know, the peak is facing the tag site. And TAGSAM injecting gas into the surface is really like a big cold gas thruster. We're also going to fire backaway thrusters. And plume impingement here on Bennu, because of the low gravity, which is about 5 orders of magnitude lower than the moon, can be very different than anything we've really seen before. Go to the next slide. So this was our first clue here about what TAGSAM could potentially do to the surface. We had a lot of ground testing for TAGSAM, quantifying collection efficiency, and in the process learned a lot about how it could disturb the regolith. Low gravity flights were a big part of the initial campaign, and there we saw that in very low G, just touching down with TAGSAM could kick material up and put it into the area where it could be entrained by the exhaust from TAGSAM. And then we also did testing in vacuum with a low density simulant, mimicking the weight, what we thought the weight of the regolith on Bennu would be, now in vacuum, unlike the 0G flights. And that photo sequence is what you see at the bottom here. Upper left, we haven't fired TAGSAM, and then proceeding down and across, you can see that when we fire TAGSAM, not only do we collect a lot of sample, we also disturb a lot of this low density simulant and project it upward. Much of it goes out on like a 45-degree angle, similar to a crater formation event, but there was definitely the potential that we could be impacting the spacecraft and parts of the spacecraft with regolith when we fire TAGSAM. That was particularly true in the what if case that TAGSAM might push through the surface and then fire below the surface. There you don't see as much of the 45 and a lot more upward motion of the regolith. So a design phase task that we had was to look at risk to the spacecraft from flying regolith impacts. If you go to the next slide. That analysis was pretty complex in that we needed to simulate what was going on inside the TAGSAM gas feed system. There we used continuum CFD. In the TAGSAM exhaust, where we used direct simulation Monte Carlo methods to understand the flow field outside of TAGSAM. We took those flow fields and then put them into a code that was written at Lockheed Martin RegoSim 2D. And that's what you see on the right is kind of a animated result for a run with RegoSim that shows particles randomly seated around TAGSAM with representative initial velocities, then what their flight path would be. And as they impact the spacecraft, we collected those statistics. In the plot on the lower left, you can kind of see a result of that. So time from fire of TAGSAM, you can pick out peaks in energy for larger particles when they'll impact the spacecraft. The smaller ones impact first at higher velocity, the larger ones later with more energy. We took those runs with hundreds of thousands or a couple million particles in each Monte Carlo kind of run and collected those up to develop a curve like the one you see in the middle that was a maximum velocity for a given particle mass that we could be impacting what parts of the spacecraft with. And we fed that into a full risk assessment activity, looking at instruments, looking at the SRC and the PICA, and looking at spacecraft structure to see whether the energies we would potentially impact with could pose a mission-ending risk. And fortunately, we found that we didn't have to take additional mitigations. The energies were low enough that nothing was going to damage the spacecraft to a point where it would end the mission. The thing we really didn't know, there were multiple looks taken at how much regolith mass in total we could disturb. Those varied by orders of magnitude based on what assumptions you made about the asteroid surface and how it would behave. So kind of anxiously awaited years later, seeing what actually happened when we tagged. If you go to the next slide. And this is what we saw. So on the lower left, you have the animation that shows coming down and firing. The photo in the middle is about the first frame after we fire TAGSAM. You can definitely see lots of mobilized regolith outside the head. We also saw in NavCam evidence of the plumes significantly disturbing the surface, and the overall disturbance was meters in diameter. We're looking at this right now. There are a few near-term papers that should be coming out that go into more depth on how much we disturbed it, how we disturbed it, and what it all means in terms of the asteroid composition. But we definitely moved a lot of material. So you wonder, well, what does our SRC look like now? If you go to the following slide. This is what we saw. We definitely saw evidence that regolith had contacted the SRC and or impacted the SRC, but no damage to the SRC. So on the lower left, you have a pre-tag image. We're basically a clean white paint. In the middle, you have an image right after tag before we stowed sample. And you see particles clinging to the heat shield TPS. We know they were just clinging there because then after stow, as we moved the heat shield and opened it up to stow and then put it back, then we get a picture afterwards that shows many of those particles have dissipated. You still see some kind of dusty smudges on the paint, but SRC is in good shape, and we've we really think we've got much more than 60 grams of sample, which is what we were required to get. So right now we're in the return cruise phase. 2023 we'll be coming back to Earth. And what will that look like? If you go to the next slide. The very short answer is it'll look a lot like Stardust. There's more to it than that, but from the beginning, we kind of designed OREX to stay within the Stardust design environments. We were building with the same thickness of TPS and a nearly identical capsule. So we wanted to stay within the Stardust environments from the get-go. OREX is a little heavier. It's coming in a little slower at 12.2 kilometers per second versus 12.5. So second fastest behind Stardust. And then the other big difference is that OREX will land in daylight, which should make it easier to find. And Stardust came in at night. So the lower left plot shows the landing ellipses. They'll both be landing at UTTR. Well, Stardust did, and OREX will. I'll point out that the OREX landing ellipse is the design 2 ellipse, and it doesn't incorporate the refinement of navigation data that the Stardust ellipse does. So we should see the OREX ellipse will shrink down as our knowledge gets closer to return.
Travis, can you wrap up a little? Thank you.
Yep. Next slide. Okay, this is basically my last slide. This is what the entry will look like as far as a timeline. Or a spin stabilized ballistic entry. Hit peak heat at about 51 seconds and peak G's at about 61 seconds. The G pulse sets up deploy of the drogue, and then the main deploy is handled by a hardware timer redundant with a pressure transducer targeting main deploy at a specific altitude of about 2,800 meters. We'll touch down on UTTR under the main with a vertical velocity about 4.6 meters per second. All very similar to Stardust. You put them side by side, and the timelines match up nearly identically. So next slide. So this is what we hope to see in 2023. This is a picture of Stardust. We really expect OREX to look just about the same with a little lighter background here. Thank you very much for listening, and I'll take any questions.
Yep, thank you so much. Okay, so there's a couple of questions. Michelle wants to know, where were the vacuum tests of TAGSAM conducted?
We did those at our materials technology lab at Lockheed Martin.
Okay, thank you. And Athel wants to know, could the TAGSAM images be used to see how well the Monte Carlo simulation results predicted the flow pattern at impact?
We're really hoping so. That's one of the things we're working on, is tracking particles frame to frame so that we can back out velocities and trajectories. But that work is still in progress.
Okay, thank you so much indeed. It's now time for the break. But I do want to ask people to take a look at the posters. And I think we're going to show the posters available right now. Tim, is that correct? And you can go take a look at the posters. They're on the website that you see right there. And the question and answers will begin after the break at 10 o'clock. So please be back at 10 o'clock Pacific time. Thank you very much indeed. Okay, are folks back?
This is Bob Moses. Can you hear me?
Yep.
Great, thank you.
See, Robert, are you online?
Yes, I am. All right. So I hope we're good for the second part of today's session on future missions, and we're now coming to the poster Q&A. The posters that you just see on the list were online, and I hope you all had time to check them out. If not, they will stay on the line for a little longer and will be documented and archived. So there is still time for later, but now it's the right time for actually raising questions. So I would suggest that we go just poster by poster, starting with enveloping aerodynamic decelerator, entry, descent, and landing technology from Kerry Nock. We've already seen the presentation. Kerry, you're on the line already?
I am. Can you hear me?
Yes, we can. So if you have questions to Kerry, please place them in the chat right now. All right, we do have one. In the case of high G loads, load lines go from the payload to the envelope equator. During the inflation process, might these lines get entangled?
That's one of the things that we're going to be looking at in the phase 2, how we actually go about stowing, deploying, and inflating the system. So that's something we're working on.
All right, thanks a lot. Another one to Kerry. How thin is the envelope to get such low IR transparency? And how would such a thin envelope be safely deployed?
So the envelope is currently about 7 microns thick. So that's pretty thin. And it's not entirely transparent to IR, but it's pretty transparent. As far as safely being deployed, there's a scrim for this particular envelope that's embedded in it. It's a composite that protects it during deployment and during entry. And if you looked at the poster, there's some images that were taken from a balloon that was deployed under the Echo 2 program, or the Echo program. This is the Echo 2 balloon that was in the order of the thickness of this, a mylar and aluminum balloon that successfully deployed. This is about a 41-meter diameter envelope, and that deployed successfully in only 30 seconds.
Great. So here's another one to you. So is the phase 2 actually funded?
Yes, it is.
Wow, that's awesome news. So there is another one. Have you considered degradation to the envelope during cruise?
The only degradation, the concern that we have is meteorites hitting it, and so we've included a cover that would protect it against meteorites. But as far as other degradation, we don't expect any. It's a polyimide, Kapton, and polybenzoxazole scrim envelope, and without it, any UV or light radiation or water vapor, we don't see any degradation parameters. We don't see any way that it would be degrading.
Thanks a lot, Kerry. So any further question to Kerry?
Thank you all for those good questions.
You're very welcome. It wasn't me. All right, and thanks a lot for your contribution and also for the awesome presentation. With that, you're dismissed. And in case that further question arise, you could chat in the chat or continue chatting in the chat. on these topics later on. Coming to the second poster, the atmospheric structure instrument for the in situ exploration of the ice giants. Francesca, are you on the line?
Yes, I am. Hi.
Hi, Francesca. So any questions to Francesca, please, in the chat. So how large of the data volume is expected from the ASI instrument to be relayed back to the carrier spacecraft?
Well, okay, that depends on the sampling rate actually, but the data volume is not such big one, and it can be easily. It will contain data during the entry phase also and during the descent through the balloon, but the volume is not such a big. It's order of hundreds of megabytes.
Thanks, Francesca. Do you expect a significant overheating of the temperature sensors due to the friction with the atmosphere? Do you plan corrections of the raw data?
Actually, there is no problem for this aspect. Actually, the friction is not really an issue. The temperature sensor that we are planning to use, that we propose, actually is the same sensor that were flown in Huygens atmospheric structure instruments on Titan. They are made by platinum wires, so it's not. This is not a problem for competition. The correction to the raw data is mostly due to correction due to the dynamics measurement of the flow, the atmospheric flow that will be performed, but it's not really problem of overheating. There is not that problem actually.
Okay, thank you. Any further questions to Francesca? I see none right now, so also here, in case that you have further questions, please do not hesitate to contact Francesca directly.
Okay, thank
With
you.
that, I would come to the next poster of today, artificial neural networks for state of charge estimation of lithium-ion batteries on small satellites, from Austin Escobedo. Austin, are you on the line? Austin, in case that you say something, we can't hear you.
Austin is not here and failed to deliver the poster.
Okay, got it. So then the next one, so I've talked to some already, so he's for sure there. And he had a poster on guidance and control techniques for Titan aerogravity assist for Enceladus observation. One in the line of the Titan aerogravity assist presentation that we also will have later in the session. Son, do you read?
Yeah, I can hear you.
Great. So questions to Son. Is the response time of the trim tabs negligible with regards to the dynamics of the direct force control?
No, it's actually not negligible, and we are modeling it. We basically have the guidance gives the command, but the controller doesn't automatically do the command immediately. There is a rate limiter and an acceleration limiter that we model in the simulation to say, okay, the guidance command comes at this rate, but it's going to really get implemented after it goes through a second order control process. So we do model that, and in fact, it's not something you should skip modeling. So we are trying to make sure we do that.
Thanks a lot, Son. And what's the dominating uncertainty for aerogravity assist on Titan? Delivery? Atmospheric uncertainty? What's your thought on this?
Well, so it really depends on what kind of delivery error we get. If we can get the delivery error, the flight path angle error that's close to what we get on Mars, even like the first Mars missions like Mars Pathfinder, where we didn't have that many assets on board, then it's totally atmospheric uncertainty that we are worried about, because, you know, as although we have had Huygens that landed in on Titan We've had Cassini flying by many times. We still don't know the atmosphere of Titan that well. So if the delivery error could be equivalent to what we got on our early Mars missions, then it is atmospheric uncertainty. But otherwise, you do have to account for the delivery error, especially if it's the type of delivery errors that we saw with Huygens, which is rather larger than what we have seen with newer planetary missions. So, and in that case, delivery error is the bigger dominating feature.
Thanks a lot. So further questions to Som? Seems none at the moment. So thanks a lot, Som. And in case that questions arise, do not hesitate to contact him directly. So the next one is EVN observations of Mars landers, enhancing knowledge of the Martian interior, from Jasper Edwards. Jasper, are you on the line?
I am.
Great. Welcome. So now questions to Jasper, please, in the chat. So first one's coming. Do the different carrier powers emitted by the spacecraft limit the quality of the inferences?
They can. The power is affected by, well, for example, to do with my own research, space weather and coronal mass ejections and that kind of thing. And that alters the power we can register here on Earth. But I'm afraid I can't be more specific than that in quantifying exactly how.
Thanks, Jasper. So further questions to Jasper? I see none for the time being. So also here, please do not hesitate to contact Jasper directly in case that further questions arise. All right, so then thanks, Jasper. And we're coming to the next poster, Neptune Odyssey mission and entry descent trajectory design. Alejandro Cansado. I hope I did pronounce that correctly. Alejandro, are you on the line?
Yes. Can you hear me?
Yes, I can. Welcome. So now questions to Alejandro, please, in the chat. Do we have any questions to Alejandro? Now it's the right time to put these in. Seems that you answered all your questions with the poster and the video already.
Excellent.
The moment there seems to be no direct question. In case that it comes up again here, please do not hesitate to contact Alejandro directly. So thanks a lot for this contribution. Let's check for the last one today. Relative navigation and landing site detection using LiDAR data for powered descent on small planetary bodies, from Harvey Gomez. Harvey, are you on the line?
Yes, how are you?
Hi. All right, so any questions to Harvey? Please put them now in the chat. All right, either my chat is broken or the people are slightly tired here in Europe or halfway already back from lunch break in the US. Any questions? So. It seems so, yes, indeed. Any questions to Harvey? I see none for the time being. So thanks also to you, Harvey, for your contribution, the presentation.
Thank you.
And in case that questions come up, I guess the email address is on the poster, so please don't hesitate to contact Harvey directly or place any question you might have in the chat at a later point in time. All right. So thanks a lot to the poster presenters and everybody who did find the time to check out what was on the website. And with that, we continue with the second part of the session of today with Rob Moses from NASA Langley Research Center. So Rob joined NASA in 1989, where he develops advanced concepts and supports mission architecture studies. He serves as the PI for NIAC study on advanced aero capture system for enabling faster, larger planetary science and human exploration missions, which he will present to us today. Robert holds a bachelor degree in civil engineering, master's in system engineering and mechanical engineering, and a PhD in aeronautics and astronautics. Robert, are you on the line?
I am.
Great. So the stage is yours. Please take it away.
Next chart, please. The executive summary is we applied well-known principles of magnetohydrodynamic power generation to create electromagnetic Lorentz forces. Forces are intended to steer the spacecraft during an aero capture maneuvers at Neptune, Mars, Earth, and other worlds with an atmosphere. The magnitude of the Lorentz forces using a small MHD patch effector away from the spacecraft center line are substantial, and in some cases as high as the whole body aerodynamic drag force. The mass of the MHD patch effector, including magnet, is on the order of the ballast mass ejected during previous Mars entries. Electrical power is also generated during the aero capture maneuver. Much additional work is envisioned, and additional funding was approved recently for continuing the subsystem design necessary for proceeding with the wind tunnel experiment to validate the analysis. Next chart, please. I'd like to orient everyone on what it means by the magnetohydrodynamic principles with this MHD basics. This is basically a flat plate with the flow velocity coming in from the left. It goes between two electrodes. And in the presence of high ionization, the ions go one way and the electrons go the other, and in the presence of the magnetic field. So that pair of electrodes generally establishes the direction or vector of the J, current density. And I'm using the coordinate system shown to the right just for this particular example. The Lorentz force is basically J cross B, and the components of that force depend on the orientation of the B field, as well as whether it's a lift or drag, depends on the orientation of the spacecraft velocity vector with respect to the flow velocity. And I'll illustrate that on the next chart, please. The alignment of the forces with respect to the spacecraft velocity vector. For the mid-L over D shape shown on the left, any force coming vertical off the surface will be perpendicular to a large extent against the flow velocity direction. On the right, for a blunt body, the force Fx acting along the same parallel as the flow velocity will actually create a lift force. And then in that case, the force perpendicular to the surface has more of a drag component. Next chart, please. What I'd like to illustrate is step through a couple of examples for Mars and Neptune that illustrate the potential or the utility of this combined CFD, computational fluid dynamics, and MHD analysis code, CFD warp. And this is a problem set up. It's basically a volumetric analysis. The footnote at the bottom is that CFD warp is a combined CFD MHD plasma sheath open source code for hypersonic and planetary entry flows by Bernard Parent, a professor at the University of Arizona. And the code can compute results in coupled or uncoupled modes. And I'm going to show you some uncoupled modes. It uses a volumetric analysis, as I mentioned. The coordinates are basically the y-axis coming out of the plane. The x-axis is the direction of the bulk flow or the flow velocity. The electrodes are shown in red. The J current density is established by those. And in this case, the B field is coming out at a theta of 90, which makes it align with the y-axis. And we looked at parametrics, basically varying the magnitude of the B field from 0.1 to 3 Tesla. And I'm going to show you some of those results. I do want to point out in bold the flow properties taken from LARA on the flank of the capsule are what's used to get the analysis started. Next chart, please. So the bold flow properties in CFD warp are interpolated from LAR results. I show here how the pressure, temperature, velocity, and molar fractions are interpolated by CFD warp and then used in the calculations going forth. Next chart, please. The first calculation is the resulting electrical conductivity in the flow and is calculated by CFD warp. In the interest of time, I won't get into a lot of this, but just to give you an idea of how these values occur, at low ionization fraction, the Siemens per meter are somewhere on the order of 10 to 100. And at higher ionization fraction shown there, they get up into the thousands. And so this curve basically shows going from the boundary layer or the surface of the spacecraft up vertical up to basically the shock layer. And you can see the change in conductivity as a result of the location. Next chart, please. This is Mars at 9 kilometers per second case. What I'm showing here are current density streamlines. That's the flow from one electrode to the other, and what the Hall and ion slip effects are causing to happen to the J current density. I've got a chart in the backup that explains the Hall and ion slip effects in more detail. But what I want to show here or illustrate here is as you crank up the magnetic field from 0.1 Tesla on the left to 1 Tesla on the right, the conductivity streamlines or current density streamlines become more skewed. And so what that does is the J cross B is it causes the force to clock around. So as you crank up the magnetic field, the force clocks around away from the flow velocity. Next chart, please. So this puts it in better clarity in terms of what's happening compared to just say your classical or basic MHD theory. The dashed black line that's almost vertical in the chart, that is what you would get for Lorentz forces for magnetic field as the magnetic field increases if you use classical or MHD theory. If you account for the Hall and ion slip effects that are present because of the rarefied atmosphere, you get some forces that are far less. What we show here are the diminished forces, and that's basically the takeaway here is that the forces are substantially less than what MHD basic theory would suggest. They're on the order of 10 to 100 times less. Next chart, please. So what does that mean for Mars? That Hall and ion slip effects are present due to the rarefied atmosphere, and these effects produce a side force that is lateral to the spacecraft surface while also orthogonal to the flow. That's what I showed you with the two volumetrics. This yields an opportunity for rolling moments and roll control and additional opportunities to implement direct force control in 3 axes. Seeding of the flow may also offer improved opportunities to modulate the forces in the light atmosphere of Mars. That's just known from the literature. Seeding boosts the density and conductivity of the flow in the MHD patch region, leading to opportunities, again, for increased control. And seeding extends the Mach range for which this approach can be used, such as for EDL to the surface. These are areas of future work. Next chart, please. Now the Neptune case, 29 kilometers per second. In this very same volumetric setup, basically the theta is going to be the same. We can actually vary the B field again, and we're going to look at 1 Tesla. And again, the electrode pair describe or prescribe the J current density and the B field, and J cross B is the electromagnetic or Lorentz force. Next chart, please. So in this case, because of the atmospheric density, the conductivity density streamlines are well behaved. They're pretty much go perpendicular to the flow across to the adjacent electrode. And as a result, the force J cross B is pretty much against the incoming flow velocity. There's no significant Hall effect due to relatively high density of the atmosphere. Next chart, please. So just to give an idea of how big these forces are, the force on the gas, these are up in the 20,000 or 2,000 or so newtons. The energy input from the gas into the electromagnetics, we're up in the megawatts. So there's an opportunity here to harvest tremendous amount of electricity from the conductive flow. But there is, as the note says, there's a heat deposited and work done on the surface as a result. And we took a first look at that initially, but that was outside the scope of this study. And so that's follow-on work. Next chart, please. So placing the forces in perspective for Neptune and Earth, an MHD patch effector having an area of 1 square meter will produce a force of about 20,000 newtons. This is comparable to the whole body drag and lift forces computed by LoRa for the Neptune entry velocity and atmospheric density. The opportunity for sizing and orientation of the magnetic field to produce the desired drag and lift vectors for controlling the entry body. And this approach seems applicable to a range of entry shapes, blunt or slender. Next chart, please. So the conclusions, the study results reveal the groundbreaking potential of this MHD approach to error capture at Neptune and Mars. Produces large forces up to or even higher than whole body drag for investigated conditions. For Mars, the low density atmosphere is challenging, degrades performance of lift and drag. However, it offers the opportunity for side force and control in 3 axes. For Neptune, forces and power generation are groundbreaking, creating new opportunities for capsule design, increased payload sizes, and faster trip times. Relevant MHD conditions for Neptune should be achievable in a flight tested Earth. Next chart, please. Future work is, just want to say again, the initial run of the fully coupled CFD plus MHD mode showed good agreement with the uncoupled results shown herein. And that will lead to the next steps, which are to conduct 3D fully coupled analysis for additional configurations and possibly other missions. Further study the Hall and ion slip effects at Mars. Further explore seeding the flow at Mars to extend the operational range to include EDL in addition to aero capture. Validate analysis results via ground-based testing. And look for flight test opportunities for Earth return entries. Funding has been approved for continuing with the preliminary design, leading to subsequent validation testing in a wind tunnel. Next chart, please. I'd like to acknowledge the study team, NIAC 1 Phase 1 study team, Neil Cheatwood, Chris Johnson, Justin Green, and Anthony Williams are my colleagues at Langley, Professor Macaret at Purdue, Professor Parent at University of Arizona, Professor Little at University of Washington, and then PhD student Matthew Alston and his advisor Andrew Aldrin at Florida Institute of Technology. Next chart is the backup slides, and you can step through. They're just 2 of them. Again, it just shows the electroconductivity equations, and then the next one will show the Hall and ion slip effects and rarefied flow for anyone who's interested. I'm happy to answer any questions.
Thanks a lot, Robert. So I see one from Atul Pradhakumar. Is the B field created by an electromagnet? If so, have the power and battery requirements been looked at in the study?
Yes, I ran the initial calculations on an electromagnet required for 1 Tesla, and its mass was pretty light. And if you can either use a permanent magnet or electromagnet, and the electromagnet mass will be a lot lighter. You don't have to carry additional mass because you get the electricity for free. And the only thing then is you have to set up the circuit so that it doesn't overheat. And that just will depend on the amount of electricity you want to use to power the magnet. And that's a trace study we have not run. We just did a simple sizing for the 1 Tesla.
Great, thanks a lot. We have time for one more question. What wind tunnel or shock tube testing of this concept have occurred?
We are looking at using high pulse at Purdue.
All right, so I take the last one from Gio. Could you downscale that to do a flight demonstration with the re-entry CubeSat, like for instance, Karman?
I did not hear all that question. I'm sorry. Say again.
Could you downscale that to do a flight demonstration with the re-entry CubeSat, like Karman?
Flight scale.
I try again without the video. Maybe you understand it
Yeah.
now better. Could you downscale that to do a flight demonstration with the re-entry CubeSat?
Oh, yeah, a cube. I gotcha. I didn't hear the CubeSat part. We have not designed or scaled this yet for a CubeSat entry. That would also be the follow-on work. But it seems like we could get some significant measurements if we were to use a CubeSat. It may have to be a 12U or something, or 16U, one of the larger ones, to get the most fidelity on the signal to noise and so forth.
Got it. Thanks a lot, Robert. So in case that there are further questions, please put them in the chat. And with that, we're going to Federico Trovarelli from Deimos Space. Federico holds a master's degree in aerospace engineering from Delft University of Technology. He joined the Atmospheric Flight Competence Center of Deimos in 2020 to work in the fields of GNC and entry, descent, and landing technologies. Currently, he's involved in the mission engineering activities for the re-entry module of the ESA Space Rider program and in the IPPW project funded by the EU to advance the TRL of hypersonic inflatable aerodynamic decelerators for re-entry vehicles, which will also be the topic of his talk today. Federico?
Hello, can you hear me?
Yes, we do. The stage is yours. Please take it away.
Okay, thanks. So thank you, Robert, for the nice introduction, and good afternoon, morning, or evening, depending on where you are in the world now. And thank you for following this presentation. So today I will introduce you to some of the latest advancements that we had in the Hefesto project. Next, please. Okay, so I want to start by introducing those of you that do not know it to Hefesto, which is European Flexible Heat Shields, Advanced TPS Design and Tests for Future in-Orbit Demonstration. So this 3 years EU H2020 project focuses on the development of the inflatable heat shield technology, and is at the moment one of the largest initiatives within Europe in this innovative field. The Hefesto consortium is led by Deimos and involves research institutes like CIRA, DLR, and ONERA, Politecnico di Torino, and also Aviospace. The end goal of the Hefesto project is to improve the TRL in Europe of inflatable heat shields for re-entry vehicles from 3 to 4, 5, and pave the way towards further improvements. The final step of the project is the design, not the realization, of an in-orbit demonstration aiming to reach TRL 6. Next, please. To reach this goal, we started from the current needs driven by exploration and access to space. From this point, we did go through several advances from design of the mission itself and system also, to also building prototypes of both the flexible TPS and the inflatable structures that make the IAD. And we also tested them from both the aerodynamic and dynamic point of view, so mechanical loads. In addition to this, we developed tools that were validated for being used in the final phase of Hefesto that, as said, consist of the definition of the IAD mission. It is important to understand that the Hefesto project is put in a technology roadmap that goes beyond the Hefesto project itself. After some trade-off, we selected 2 mission case scenarios that can drive the development of IAD technology for Hefesto. One is the high mass ballistic entry on Mars, and the other one is the recovery of the Avum Vega upper stage in the atmosphere of Earth. This presentation will focus on these two missions, and in particular on the mission analysis aspects that represent the connection hub for the requirements and constraints which arise from the development of both the flexible TPS and the inflatable structure. Next, please. So for the Mars application, the robotic exploration mission layout consists of a direct Mars ballistic entry and combines the hypersonic deceleration of the HIAD with supersonic retropropulsion. The idea is to deliver about 3 tons of payload at a landing altitude larger than MOLA 2 or even 3. Next, please. After several design loops with ONERA, which is responsible for aerodynamics, and DLR and CHIRA, which are in charge of the system aspects, the configuration of the Mars entry module reached a consolidated configuration. In particular, the 6-ton entry module features a HIAD of 9 meters of diameter with a cone angle of 140 degrees. The payload is approximately 2.5 tons in this configuration. Next, please. In addition to these inputs for the mission analysis, the team also converged to a set of aerothermodynamic and mechanical load constraints that allow us, Deimos in particular, with its with the LEC proprietary tool, to define an entry corridor in terms of ballistic coefficient and flight path angle at entry interface point. Now, I know that this graph is a little bit scary, but it's also very useful because each line is an isoline of a specific value of a variable which is related to the entry trajectory. Some of these isolines can be used as our constraints to determine an envelope, which is the gray one that you can see, whose points, again, in terms of ballistic coefficient and flight path angle, do not violate any of these constraints. By taking the reference ballistic coefficient, it is possible to determine, using this graph, the steep and shallow limits for the flight path angle at entry interface point. As expected, the steep flight path angle is limited by the maximum heat flux that the HIAD can stand, while the shallow limit by the estimated landing accuracy and the maximum heat load. Because in fact, when the flight path angle is shallower, normally the flight extends in duration, and this happens. Next, please. So with this slide, I want to show some of the results that we got from the Monte Carlo campaign that we ran for the entry trajectory on Mars. In particular, on the left, you can see the heat flux for the Monte Carlo trajectories, and on the right, the heat load. We want to demonstrate with this that the Monte Carlo campaign confirmed that the peak conditions are within the limits of the sizing trajectories of the local entry corridor. And also, they are in line with the material sizing conditions that were determined by the analysis run by Aviospace, which is in charge of the material characterization for the Hefesto project, and also within the heat flux values from the DLR ArcJet test campaign, which was presented in more detail by Dr. Esser in one of the previous IPPW sessions. It is interesting to notice that for relating the stagnation point heat flux with the cone heat flux, we used a margin approach, and the factor that we defined in agreement with all the physical mechanisms that go on during the reentry, which involve catalyticity, turbulence, chemical reactions, and so on, have been proved consistent by a later CFD analysis run by ONERA. Next, please. The Monte Carlo campaign additionally confirmed that the terminal SRP guided phase is capable of guaranteeing a successful landing irrespective of the perturbations that were considered. So atmospheric conditions, we used different atmospheric scenarios, and vehicle properties, so aerodynamics and mass specifically. Next, please. Some additional theoretical Monte Carlo analysis have been carried out also to assess the performance limits of the design mission architecture. The graph on the left shows how the SRP fuel mass varies as a function of the Mach at IAD release, while the graph on the right gives an idea of the maximum theoretical molar altitude that can be achieved by anticipating the IAD release. From this analysis emerged that diving deeper into the atmosphere with the IAD, which would require it to be dynamically stable at lower Mach numbers, would allow to further increase the payload to fuel ratio. On the opposite side, an early release of the IAD followed by an early SRP phase at full throttle could make it possible to land at higher molar. This analysis showed that in general, the mission architecture based on IAD and SRP is extremely performing and can be tuned to different mission needs. Next, please. For the Earth application, the mission layout for the recovery of the AVUM Vega upper stage consists of a deorbiting from SSO orbit, a controlled lifting phase, which of course requires lift, and combines the use of the hypersonic IAD, followed by a parachute supersonic deceleration, and finally a parafoil phase that allows to bring the entry module in the area where mid-air retrieval is planned. Next, please. Also in this case, the design loops with ONERA, DLR, and CHIRA led to a consolidated configuration for the entry module that consists of the about 1 ton AVUM stage, which is protected by 4.5 meter diameter, 4.75 meter diameter IAD. Next, please. So again, we exploited the LEC tool, and this graph is analogous to the one that we already seen for the Mars case. The value of aerothermomechanical isolines was obtained in this case for angle of attack equal to 0, which is a conservative assumption for these aspects. As expected, the possible entry flight path angles are much shallower than for Mars, that has a less dense atmosphere. The shallow flight path angle is limited again by landing accuracy, while now the maximum tolerable G load is assumes a fundamental role in limiting the flight path angle on the steep side. Next, please. For generating lift, which is used during the entry phase, it was decided to give the entry module a COG displacement, so that this can result in an angle of attack that allows to steer the vehicle towards the landing site. From this, we designed, we looked the design for the definition of a range capability, also in consideration of aerothermodynamic and mechanical constraints. The entry interface point dispersion for the AVUM upper stage, which is given by Avio, is much larger than the dispersion that we would have at landing. But we verified that a guided lifting entry followed by also the parafoil phase, the guided parafoil phase, allows to be compatible with mid-air retrieval capability with a helicopter. Next, please. So, in light of what has been presented, the IAD system represent an enabling technology for the next class of Mars exploration missions compared to state-of-the-art. The enhanced drag provided by the IAD will allow to increase both the landed mass and the molar altitude where soft landing is possible. From the Earth point of view, the IAD is confirmed to be an appealing, performing, and robust solution for the purpose of safely returning the Vega upper stage to a targeted recovery area. This class of system can be key in reducing the cost of access to space through upper stage reusability. Next, please. So, the results of the Hefesto project in general confirm the need for advancing the TRL of IADs in Europe. The relevance of an IOD mission that will enhance and consolidate the European know-how in the field, of which at the moment the Hefesto consortium represents the core, is also reinforced. The next step of Hefesto consists exactly of this, as I already said, designing an IOD for the AVUM recovery that can merge requirements from both Earth and Mars cases, and also the different disciplines from Hefesto. The realization is at the moment out of the scope of the Hefesto project, but we hope it could be a continuation of it. Next, please. The Efesto Consortium is in fact the core of IA technology in Europe and is developing fundamental know-how not only in the design of this class of systems, as we have seen, and their exploitation, which is what Deimos is responsible of, so the mission analysis, but also in testing and manufacturing them, which represent two key aspects for a future commercialization of analogous products. Next, please. So yeah, with this, I ended my presentation and I wait for questions.
Thanks a lot, Federico, and also thanks a lot for keeping so nicely the time. So if we have any questions for Federico, please put them in the chat right now. If there is none, then I actually do have one. Did you look into scalability of this technology also for larger upper stages for Earth entry? How would that work? What's your view on this?
So basically, we studied these two missions specifically, and in particular the one for the Earth, only for the AWUM. But because the focus of the project is to develop the technology in terms of materials and structure. But we expect that after this first step, the following investments and also the IOD could lead to further developments in the field, and for sure also to larger payloads, because also on Mars we have a much larger mass, so theoretically we think it's possible.
Great, thanks a lot, Federico. So with this, I would like to go to our next speaker then. Next speaker is Jim Arnold from AMA at NASA Ames. Jim, are you on the line already? So Jim has worked in the fields of atmospheric entry technology for 59 years, starting with his study of radiative heating for the Apollo Command Module under the leadership of Alvin C. Amongst various other achievements, he served as the chief of NASA Ames Space Technology Division for 14 years and received many awards, including also the IPPW LCP Award. Today, Dr. Arnold will be talking about heat shields for aerogravity assist vehicles whose deceleration at Titan saves mass for future flagship class exploration of Enceladus. Jim, can you hear me? Mic check. Jim, I don't hear you.
He was present the whole day this morning.
Yeah.
Yeah.
Can you hear me?
Yes, we can.
Okay, good.
Hi, Jim. Stage is yours. Please take it away.
Thank you for the introduction, Robert. And I want to say first that we greatly appreciate the opportunity to talk about Titan aerogravity assist maneuver and the benefits that it can provide for the exploration of Enceladus. Let's just take a moment and look at this beautiful Cassini image of the Enceladus and its geyser spouting from the South Pole. Scientists have analyzed the Cassini measurements and find that the ingredients for life exist on Enceladus: carbon, hydrogen, oxygen, and nitrogen. It has a global ocean and a rocky core. Moreover, the acquisitions of samples is very easy on Enceladus. We acknowledge here our co-authors and note that their skills include mission architecture, life sensor development, and atmospheric entry technology. Next chart, please. So this is what we'll talk about today. We're going to show some highlights from the Spilker et al. 2009 Enceladus mission study, and they made the point that aerogravity assist is enhancing for Enceladus studies, and it's just using a conceptual blunt body. We're going to talk about two white papers for the 2023 decadal survey that show that heritage blunt bodies with high TRL heat shields are suitable for Titan aerogravity assist. We're going to make an observation that the use of Titan AGA could shorten the 2020 Orbit-Lander mission concept by McKenzie and her colleagues by 2.25 years. Next chart, please. So let's look at these bullets on the lower right-hand side first. Habitability of Enceladus Ocean was suggested by Cassini measurements. There was a 2018 NASA roadmap to ocean worlds that strongly recommended a search for life mission to Enceladus be a high priority for the next decade. And we're going to show here some of the results from the 2000 analysis by Spilker and his colleagues. These were done so that the concept would fit in the New Frontiers cost and time cap for Enceladus exploration. It was shown that Titan AGA would enable us, including a 2.25-year moon tour. We'll talk about that in a minute. There have been many prior studies of Titan AGA, and those are listed in our references. But the two we'll talk about today go much more in depth than is required to look at the technology. Look at the upper left-hand corner, and you can see the trajectory of getting from the Earth to Titan. It requires 9.3 years time of flight, and it also involved 4 gravity assists, 2 at Venus, 2 at Earth. When you approach Titan on a hyperbolic trajectory, you then dive into the atmosphere and exit the moon of Titan in a different hyperbolic trajectory, targeting to begin the moon tour. The important thing that Spilker and his colleagues presented was the idea that a mission-enabling blunt body could be done with AGA. The concept that they showed in their paper is indicated here in the upper right corner. The moon tour basically requires 2.25 years, and this is where you go from the orbit of Titan, shown in red there on the lower right corner on the moon tour figure, to where you reduce your energy to become in the area where you can do studies from Enceladus. And these studies, according to the mission study by Spilker and his colleagues, showed 9 different missions that would study the ocean from either orbit or with landers or combinations thereof. Next chart, please. So here we're going to give the high-level results of 2 of these 2023 decadal survey papers. To the left, we talk about the heat shield. To the right, we talk about GNC, guidance, navigation, and control. Let's look at the bullets on the lower left first. Titan AGA was studied with a 60-degree sphere cone, 5-meter base diameter, 3,800 kilograms mass, a ballistic number of 128 kilograms per meter squared, and the trajectory was done in 3 degrees of freedom using an Ames in-house triage code. Peak heating, pH, and heat shield mass fraction, HSMF, depend upon how you intercept the location of the spacecraft with Titan's orbit. The heat shield mass fractions were estimated from stagnation point sizing. We discovered that low heat shield mass fractions could be done with the TRL9 TPS phenolic impregnated carbon ablator pica. For the 2 lower speeds that we studied, the TRL heat sheet for extreme entry environments heat works the 9 for the 14.81 kilometer per second case. My colleague Raj Venkatapathy will be talking more about these TPS materials in the following talk. Let's look at this diagram in the heat shield area. First, we note that when the spacecraft approaches Titan nearly perpendicular to the moon's velocity, the peak heating is 460 watts per square centimeter. The heat shield mass fraction is very low, a little over 5% using pica. The middle diagram shows the case where Titan and the spacecraft are going nearly in the same direction. The peak heating drops to 117 watts per square centimeter, and the heat shield mass fraction climbs a bit because of the increased heat load. Looking to the right, we see a very aggressive case where Titan's velocity is nearly perpendicular to the spacecraft's. Here, the peak heating jumps to 2686 watts per square centimeter, and the heat shield mass fraction is 26.2%, requiring the heat TPS material. That 26% is doable because Stardust had a 22% heat shield mass fraction. Let's look to the right now, and the bullets on the lower right. This is the work that was done by Tackett and his colleagues, and also I'd like to point out that there was a poster session by some in this session just a few minutes ago. Titan AGA was done with a 6 degree of freedom with the post-2 code, which has a Langley heritage. for the high-speed case. The Heritage 70 degree sphere cone was based on MSL and had a ballistic number of 150 kilograms per meter squared. In the paper, it's said that GNC will work for other Heritage pump bodies in addition to MSL. For example, the Apollo shape or the Genesis shape that's now baseline for the Dragonfly mission. Also, it was shown that by looking at the difference in energy between Titan's orbit and that of Enceladus, that the propellant load could be reduced by 99.5%, not accounting for the presence of an aerogravity assist aeroshell. Look at the diagram at the top, and we can see a little bit more about this AGA maneuver. For the high-speed case, you enter on along a hyperbolic trajectory at 14.81 kilometers per second. You then dive into the atmosphere at 1,200 kilometers, and you do active guidance throughout the aero pass. And when you exit the atmosphere at 120 kilometers, you're heading for a different hyperbolic trajectory, aiming for the moon Rhea. This minute mover is similar to aero capture, but different because you're targeting for a different hyperbolic trajectory. Next chart, please. So here we make some observations comparing the 2009 study by Spilker and the 2020 study by Shannon McKenzie and her colleagues. It's called the Orbalander mission, and the Orbalander is given that name because it does science both from orbit and on the surface. A concept for the Orbalander is shown to the right with the conical sample collector there that collects the ice crystals. They have required a 7-year time of flight to the Saturn orbit using the SLS system and a high energy Castor 30B upstage. This required to get that time down, a Jupiter gravity assist to shorten the transit time. They had a low-cost alternative, a 9.3-year time of flight, using a Falcon heavy expendable launch vehicle, and this required 2 Venus gravity assists plus 1 Earth gravity assist. They did not consider Titan aero gravity assist. This required them to go to a 4.5-year pump down called the Moon Tour. Contamination control was considered against two sources: the bioshield for the terrestrials. If you look at the lower right corner, you can see the bioshield, and this protects from the time the spacecraft is sterilized until it exits from the environment of Earth. They avoid against the Titan's organics by staying a safe distance from Titan. This contrasts to the study by Spilker, where they did consider Titan aerogravity assist, and that required only a 2.25-year pump down, half that was required for the Orbalander study. We make some observations here. If this emerging bioshield technology could be extended from the sterilization to the exiting from Earth area to be used from the launch to the post-Titan AGA, and if the in-cruise bakeout studies that are being done in reference 11, contamination control might be acceptable to the astrobiologists, and this would allow the use of Titan aerogravity assist for Enceladus exploration. If so, Titan aerogravity assist could shorten the duration of the McKenzie study by 2.25 years. Next chart. So in summary, we've shown the results from 2 white papers from the 2023 Decadal Survey that support the hypothesis by Spilker that a blunt body aerogravity assist is enhancing for missions looking for life signatures in Enceladus ocean. That is, they have low heat. We've shown that they have low mass heat shielding, can be done with high technology readiness, TPS materials, and that the AGA maneuver using modern GNC techniques is doable with heritage blunt bodies like MSL. If we compare the 2009 and 2020 mission studies, this suggests that the Titan AGA could significantly reduce mission duration and propellant load for the Enceladus Oberlander mission presented by McKenzie and her colleagues. Contamination control of the aeroshell by Titan's organics is a remaining issue that must be addressed if we're going to use Titan AGA for Enceladus missions. This could possibly be done by advancing the present bioshield technology that's being used against the source of terrestrials. We would suggest a preliminary study for the look at the mass benefits for science instrumentation and reduction in mission duration that could be achieved by flying the bioshielded Orbelander in a heritage body during the Titan AG. This would be followed by a separation of the aeroshell and the Orbelander during the main tour, crash the AGA or aeroshell into one of the moons, and then deploy the sterilized Orbelander to Enceladus. Next chart, please. I'd like to say that the figures that we've shown here are from the cited literature. They were done under the authors conducting research funded by most cases. In most cases, the figures were approved by the lead authors of the publication we've referenced. Gary Allen and myself appreciate the funding for this research on Titan aerogravity assist that was provided by NASA Ames under the contract number that's specified there, and by Dave Corneliuson, our supervisor at AMA. Next chart. Next chart. This shows a list of references, and with that, we conclude our presentation. Thank you.
Thanks a lot, Jim, for this great presentation. So we do have time for a quick question. So here it comes. Great talk. Did the study look into using high arrival speed interplanetary trajectories, which could lower the flight time even further?
Say it again, please.
Did the study look into using high arrival speed interplanetary trajectories, which could lower the flight time even further?
No, if you recall, the study by McKinsey et al. Used a gravity assist by Jupiter, which reduced the time frame, including also the very energetic launch vehicle, to a time of flight of 7 years. There was no further study of that done that I am aware of.
Thanks, Jim. Any further questions to Jim? I see none for the time being. So in case that you have further questions, don't hesitate to send him an email. Thanks a lot, Jim.
Thank you.
So with that, we're coming to our next speaker, which is Ethiraj Vendakrapati. He's currently NASA's senior technologist for entry systems and also the chief technologist for the entry system and technology division at NASA Ames Research Center. Over the years, he has been one of the driving forces for preserving existing TPS know-how whilst advancing on various new technologies. He's currently focused on sustainability of NASA critical ablative TPS for future missions and working on advanced ablative TPS technology to enable aero capture missions. In this context, we will be talking today about thermal protection system to enable Ice Giant aero capture mission for delivering both an orbiter and an in situ probe. This talk would have been actually his third final technical talk at an IPPW if I wouldn't have messed it up with shuffling the program on the last minute. Apologize for that. Raj, please take it away from there.
Thank you very much. Thank you. Great session. I really enjoyed Dr. Noak's earlier presentation, also Bob Moses's. So the topic here is more mundane and considering the amazing presentations they gave. First, I want to recognize my co-authors that are listed in this chart, and we are all from associated with NASA Ames. Let's go to the next chart, please. So this is the recommendation. Hopefully I have time to walk through the charts to get you the data as to what the recommendations are. The HEAT, which is the heat shield for extreme environment technology, it is ready. It is today adopted by Mars Sample Return Mission Earth Entry Vehicle. It's at TRL-6. This is capable of doing Neptune aero capture to not only get to Neptune, deliver probes, but also Triton, get landers to the surface. But it may be too heavy, considering the entire design space. So what you will hear is more efficient TPS that are high maturity level that could be, the development could be completed rapidly to allow for mass efficient and enabling TPS for aero capture. So with that, let's go to the next chart, please. So you've heard a lot about Neptune, Triton, aero capture, why it's important, why ice giant is important. Triton being a irregular moon, it is a captured object by Neptune. It has potential life forms, potentially for, and so there's a lot of interest. And this has been looked at, studied various times in the last 30 years, actually, aero capture. This is not new. And the last study that was done pointed out some of the challenges. The picture that you see on the top right-hand side is one of the middle-lower geometry that was studied. What is new about this since that study was done really is that study pointed out the lack of thermal protection system to close the mission, so to say. The heat fluxes were enormous and the heat loads were enormous, that even carbon phenolic, which wasn't available when the study was done, even if you had revived it, it would not close. But in the last nearly 20 years, advances have been made in across the board. And that's what allows us today to assess whether we have the right TPS capability today to enable a ice giant aero capture mission, specifically Neptune, in the coming decade. And let's go to the next chart, please. So recently there have been a lot of work published to identify fast missions. If you can get there fast, you can use then radioisotope power systems also. They have a lifetime. So the combination of looking at fast missions, if you can get there fast, that means you have to slow down. Propulsive insertion, you have to carry propulsion mass, the fuel, and that only allows you to a certain arrival velocity. This is the hyperbolic excess velocity when you get to that planet. For Neptune, the computations that have been done, the chart that shows on the left-hand side by it was Atul's work that embodied also JPL's work, and that shows that if you do aero capture, even with a low L over D, moderate L over D, a blend body, you can get there. And the opportunities are plenty between the 2030 and 2040 time period. By the way, I'd like to congratulate Atul for getting his doctorate. Now he's Dr. Girija, so congratulations. So with the kind of arrival velocities, if you can use aero capture, then you can also do a lot of things. It's mass savings. And now with the additional mass that's available, you can do not only the insertion, but also deliver probes and landers after you have done investigation around the planet. This is what makes this more scientifically attractive. Galileo probe was done without knowing what the Jovian environment is going to be. It entered the spot which was dry. A lot of the scientific data could have been better if we were able to do that from orbit. That is the logic here, that the science community that wants to do both orbiter and probes can benefit from that. The right-hand side, you see the geometries that we have considered. MSL, for example, is flying at a LORD of 0.28, but for enabling these missions, you need to be higher, around 0.4, 0.5. The geometry that you see on the very right-hand side on the top figure is called ACV, and that is a optimized geometry that was looked at for Orion in 2005 timeframe. It was optimized not only from the GNNC controllability perspective, but also from TPS perspective. And a lot of work that was done is being leveraged in this study. Let's go to the next chart, please. So given that we want to do aero capture around Neptune, we want to do that with a moderate LORD of 0.4-ish. What we then needed to do is, how do we do this? Look at this design space. Different velocities, we can get there, different mass, different geometry in terms of the diameter. So we wanted to do a much more broad global investigation rather than a point design study that was done in the earlier 2004 study. So the way we went about is the following. For every given mass, diameter, arrival velocity, and you can then determine what the overshoot and undershoot trajectories are for getting through Neptune and then arriving at Triton. It's just that trajectory. So these two trajectories essentially bound all the other trajectories with the lift modulation. So the chart that you see at the bottom left is the overshoot undershoot trajectories for arrival velocity v infinity of 22 kilometers that translate to a v inertial velocity or relative velocity close to 35 kilometers a second. With that kind of speed, now you can see for a 3 meter to 5 meter diameter, 22 kilogram, what these altitude versus time would look like. These were all done with a 3DOF simulation. So I'm using that geometry I showed earlier, aerodynamic characteristics are here. We can repeat this exercise for other velocities. What we decided to do is look at 8 kilometers, 14 kilometers a second, 22 kilometers, and 25, 18 and 22. Yeah, 14, 18, 22. These four velocities essentially bound and reduce arrival time anywhere between 12 years to 8 years in that previous plot I showed. But when you enter Neptune, when you exit out of that, all of these trajectories achieve a 25 kilometer exit velocity, which puts that into the orbit to intersect Triton. Okay, let's go to the next chart. So now that we have defined a broad design space and how to bound the trajectories, next is to define the aerothermal environment. The way we did that is to look at each of these trajectories, 24 of them, bounding the entire design space, and then did some CFD for each of those peak, the lowest altitude, the peak heat flux point, where we can look at an angle of attack, what would the heating be like? For the 22 kilometers a second, this is 35 relative velocity that you would see the picture on the left-hand side you see on the top. That's the heat flux distribution from a CFD solution. And when you fly at an angle of attack, the stagnation point is more towards the shoulder at the bottom. You see that. The distribution is very uneven. Windward side has much higher heating localized. The rest of the body is much lower heating. Also, in the trajectory code that we have, built-in engineering correlations we can use if we can relate the stagnation point local curvature, essentially, to an equivalent spherical nose radius, which is what we did using CFD. With these two combinations, CFD and trajectory simulation, we can now define for the entire surface correlation functions of heat flux pressure and all of the other quantities. Now we are ready to do the TPS sizing. But before we go there, one question comes up, which is, could the flow become turbulent? If it is, it complicates the life, because then we have to decide, okay, where is it going to become turbulent, how much augmentation, etc. It so happens that the entire trajectory space we look at for all of these cases, the lowest altitude, we can look at that for the highest ballistic coefficient and determine whether it's going to become turbulent. That's what is shown on the color plot, the contour plot you see at the bottom of the left-hand side, which is a Reynolds number based on the roughness. And that is so low that because the pressure is very low, the density is very low in all of these trajectories, that the chances of flow becoming turbulent, even for 5 meter, is extremely small, So that the laminar solution, the solution that we have from CFD and integration, can allow us to then start to look at what kind of TPS we want to use. The bottom right-hand side plot, which shows the peak heat flux along these trajectories, you have the undershoot and the overshoot trajectories. One of those defines the peak heat flux. The other one will define the peak heat load for the entire trajectory. So first thing we do is to look at the peak heat fluxes. They range from 250 watts all the way up to 2,700 watts, that plot that shows stagnation. So now, before we say we're going to do the TPS sizing, we can ask the question, what's the TPS we have, state-of-the-art TPS, and what are they capable of that can we size with them? Let's go to the next chart, please. So heat, you've heard a lot about it in the past years. It's a 2-layer 3D woven system. It has been developed and demonstrated at 1 meter diameter scale. The photograph on the top right, top left shows that. In addition to heat, which is a TRL6, so we can definitely use them for these missions, but it's for extreme entry environment, the environment that we are seeing here are not that extreme. So when we look at that, then we say, what else can we use? This is where Pika is, which is a TRL9 for, you heard OSIRIS-REx, that's a Pika solution, MSL and Mars 2020. But for 3 meter to 5 meter diameter, Pika has to be in tile form, but the gap, the seam that needs to be filled, that solution for the kind of heat fluxes we're talking about, they're not matured yet. We have done preliminary work to look at that. Conformal Pika is another material that we have developed at TRL 4-5, so to say, 5-ish. And that is much more efficient compared to Pika. It's the same density. That also has been, the seam solutions have been done at smaller scales, but for larger scales that we need to look at. We have tested that for around 750 watt stagnation point conditions, 350 watts of flank regions, and so on. In addition to heat dual layer, the heat dual layer has a top layer, which is very high density, and the inner layer or insulating layer, that's a much lower density. The inner layer also has been tested at all the facilities we have, and it is equally, the facility limitation is essentially part of this. And at those conditions, 3,500 watts and 5 atmospheres, it behaves equally well, equally robust. So we can look at all of these materials for these missions and then decide. What you see on the bottom right-hand side is the plot that shows for these various cases, essentially what the peak heat flux is going to be. This is a stagnation point. So,
what is the time?
Okay, majority of the conditions are going to be below 1,500 watts. For that, we can use conformal Pika or Pika. Above that is the challenge. Do we need to go to heat 2-layer or single layer? Let's go to the next chart, please. This is essentially my last chart. So when we take a look at these heat fluxes, we also need to take a look at heat load once we have decided which. And the heat loads, you will see the top left-hand side plot ranges for these excess velocities somewhere between 75,000 joules per centimeter square all the way to 500,000 joules per centimeter square. And those are the kinds of defining things. When we use 2-layer heat, we come up with a mass fraction range from 22 to 67%. But majority of the cases are quite doable with conformal TPS. When we do that, you see on the right-hand side plot, CPICA, that is the lowest areal density that you would see. This ranges from 5 to 15% in terms of those cases where they're applicable. But when we go to higher heat flux cases, peak, we can do now dual TPS. The bottom half, we can use CPICA, and the top half, we can use single layer heat. That's what is shown in the middle orange one. So with this, I just want to make sure that we have a capability we can further develop, which is engineering. If we did that for ice giant missions, we would have a mass fraction ranging from somewhere between 5% to 20% or so. That can easily accommodate all of these, not only a big orbiter, but also probes and landers. Let's go to one chart. It's acknowledgement. I just want to recognize that a lot of this TPS development takes decades. It's not simple. It is a whole ecosystem that's involved. I just want to recognize people that contributed to the various TPS that I showed. Thank you very much.
So thanks a lot, Raj. So we have one question in the chat for you right now. So Greg from Abu Great to see the very encouraging TPS mass fraction results for aero capture at Neptune using single layer heat. This will certainly be a useful reference for future studies. Not sure if this is a question to you or a comment.
So the last chart I showed, which gives areal density, that's primarily the reason how people can use that areal density as a function of heat load to be able to design with it. That's why we did that, because it's not very easy to look at all of these various cases to do. So thank you very much for that comment question.
Great, thanks a lot, Raj. And if there are further questions to Raj, please do not hesitate to contact him directly. And with that, we're coming to the last speaker of today. I've seen Richard already on the line. Richard is now the Director of Business Development and Strategy for Space Systems at Rocket Lab USA. After spending several years at JPL, including a stint at NASA headquarters STMD. He will be talking about Venus 2023, a photon-enabled planetary small spacecraft mission for decadal science, as already announced in Sarah Seeger's talk earlier today. Richard, stage is yours.
Thank you, Robert. Appreciate the opportunity to share a little bit about what we're doing with Venus. And I'm going to go pretty quick. So if whoever flipping a chart could, I'll call those out. So if you want to go to the next chart, just a little intro of myself. As Robert was saying, I spent a good portion of my career at JPL and did a stint at NASA headquarters. But I guess what I'd like to say is it's really exciting to be back with the EDL community. I participated in a number of IPPWs, Barcelona, Atlanta, and it's just really great to be back with this community talking about a small probe mission. So next chart. I think folks hopefully are aware of Rocket Lab as the global leader in dedicated small launch, but we are working to basically move up the value chain with our integrated satellite system called Photon. And so I'll just give you a high-level view of what is happening with space systems at Rocket Lab before moving into discussion about the Venus probe mission we have in development. Next chart. So, we're a vertically integrated space company. We've got our headquarters in California in Long Beach, but we've got a pretty cool footprint with our Sinclair Interplanetary acquisition in Toronto, and then a fair amount of capability, particularly on the launch vehicle side in Auckland, as well as our two launch sites, one in Virginia and another in New Zealand. And so, vertical integration is an important theme at Rocket Lab that we apply across our space systems division as well. Next chart. So Electron is our workhorse launch vehicle, and what's pretty amazing about this vehicle is that it actually is capable of enabling dedicated planetary missions. And so I won't go into details of this rocket. There's a lot of great tech in it: carbon composites, additive manufacturing. Of course, it's a battery-powered rocket. The electric fuel pump-driven engines are pretty innovative, but we're here to talk about probes. So if you want to go to the next chart. And it's built a huge amount of heritage, and so this is a vehicle which is Category 1 certified, and basically our story is that small launch is a solved problem, and now this is a tool that we have in the kit to do really cool missions with. Next chart. The kick stage is a bit that I'd like to draw your attention to. This is the third stage of the vehicle, and it's important because it's built a huge amount of heritage for key capabilities like in-space propulsion. This is really the heritage and the foundation upon which the Space Systems Division is built. And if you look at the equipment on this vehicle, I think it's pretty easy to see how we can take the next step by adding some key equipment to have a full satellite solution. And so that's what we've done with what we call Photon. Next chart. And so, Photon it represents a family of vehicles. It's we like to say a configurable spacecraft. And so whether we're designing something that needs to fit within the mass constraints of Electron, or something that can fly on a vehicle like Neutron or medium lift vehicle that we have in development, or as a secondary payload on other launch vehicles. We've got the ability to scale to different mission requirements. Some key capabilities, that in-space propulsion that I mentioned, and a new engine called Hypercurie that we have in development, I'll talk a little bit more about. Next chart. So we launched our first Photon last year. Actually, we almost have a year of heritage on it now. Really successful mission, demonstrated that step up from a kick stage to a full satellite platform, demonstrated a lot of the key subsystems we needed to add, and of course was a very successful mission in of itself. So we go ahead, next chart. We watched, rinse, and repeated then on our second Photon mission called Pathstone. And what was cool about this one is it actually is a risk reduction mission for the Capstone mission. And so I'll talk a little bit more about Capstone. It's our first mission to the moon, and this vehicle, Pathstone, basically did the same thing that First Light did, which is deploy a customer satellite, operate as the upper stage of the launch vehicle before turning into a satellite. But it's flying a lot of the avionics and software that are going to be required on the Capstone mission. So working to de-risk that in orbit right now. Next chart. So we're really excited to be taking NASA to the moon. This is the first launch of the Artemis program. On the next chart, if you want to flip forward, there's a couple images of what we call high energy Photon. It's basically a souped up version of the kick stage and Photon with large propellant tanks and a new engine called Hypercurie. If you want to go to the next chart. This mission is pretty cool because we launch into orbit on a dedicated vehicle, and then we slowly raise the apogee over about 8 days before targeting the escape burn. And so this allows the escape asymptote to come into alignment and to very precisely target the escape conditions. So this model is the same one that we'll use for the Venus mission and basically all the missions that we would plan to perform planetary missions with Electron. For Capstone, we'll deploy the customer satellite and it'll go off and do its tech demo for Artemis. But on our mission, we'll take advantage of being on this escape trajectory to the moon to go do our own flyby and shake out those deep space capabilities that we need for follow-on missions. Next chart. So one of those missions is Escapade. So we're sending 2 spacecraft to Mars. Rob Lillis at Berkeley selected us, and so this is a pretty important mission to continue to develop our deep space capabilities, many of which are required for Venus, in particular an X-band communication system that will be flying on the Photon that's going to Venus. There's a lot to say about this mission, but I think what I'll just highlight is that this kind of demonstrates our ability to fly different platforms. This will fly as a rideshare on an Esper ring, and so that pair of vehicles will be flying on a NASA-provided rideshare launch. Next chart. So, we're here to talk about Venus, and so I want to just give a couple messages about what we're doing and why. So, this is a private mission to Venus, and if you want to go to the next chart, I think it shows what our objectives are. The key one is, are we, the most important question. We want to help contribute to that. If you want to go to the next chart, please. Part of the reason I joined this company, and a lot of our leadership feels the same. Pete, Doug Sinclair, our tech fellow, S.M. Mosley, our chief engineer, and a lot of folks are inspired by the same thing that all of you are, which is civil space science and contributing to answering some of the biggest questions. And so we want to do that with this mission. It is to look for life. We've been working with Sarah Sager and her team as you heard earlier today to understand how we can use this capability to actually contribute to science. And we do think that it's high impact science, decadal class science. Beyond contributing to that science question, we do want to demonstrate capabilities, and so a small probe capability that could be used to for a myriad of applications and at different destinations. We are committed to going, so we've made the commitment on the vehicle, on the satellite, and you can see just a high level how we're building that capability up with Capstone and other missions to be able to prepare for this. And we hope it's just the first step. We think dedicated launch of small spacecraft is going to be really important to increasing the regularity of planetary science. And this mission, we hope, is just a first step in a campaign of missions, particularly to Venus, to contribute to that big science question. So that's what we're trying to achieve. Next chart. So let me show you like what the plan is. So currently we are targeting a 2023 launch window, and of course this is an aggressive schedule to meet, but we are working towards that right now. The mission is a hyperbolic trajectory, and so we don't plan to go into orbit with our assets. We'll just fly by and then plan a direct entry of a probe into the atmosphere. We are using this high energy photon, similar to the Escapade mission and Capstone as a satellite. But for this one, it'll have a very important function of acting as a communications relay with a probe. It's a small probe, no more than 20 kilograms, with just a few kg allocated for instrumentation. And our science objective is in the clouds. And so we're targeting that a few kilometers, 45 to 60 kilometers in the cloud layer. Next chart. So this is the mission architecture. I've identified a few of the pieces already, and I'll go in and actually in subsequent charts on each of these, so we can just keep going in the interest of time. This is the preliminary concept sitting in the launch vehicle, and so you can kind of get it for scale in a standard electron fairing. Next chart. Probe shape is always an important discussion, as this community knows well. And so we are notionally converged on the DS2 shape with a 45-degree half cone and hemispherical aft body. The name of this game is simplicity. We're not planning a pressure vessel. We're not planning a parachute. We're not planning a heat shield. We want to basically do the least possible, but still show a capability that meets a science objective. And so this shape is a useful one for meeting that overall goal of managing complexity. Next chart. So this is just a cutaway view of the current concept. It does use an in situ sampling system to feed gas from the forebody into a representative instrument that we've been working with. So you can see the key features here that you've been hearing already in this conference today, with heat and some other enabling technologies that we hope to take advantage of. Next chart. So there are a couple instruments that are under consideration. Including these should by no means suggest a collaboration or any kind of agreement to provide these. I'm assuming that Sarah, well kind of captured the current thinking and status of collaboration, but we wanted to use a couple different instruments that we knew had high science return to basically demonstrate and go through this preliminary design exercise. And so we're considering both the mini TLS, which obviously has heritage from Mars Curiosity and other missions, and then this autofluorescing nephelometer, which adds a lot of really cool science, not just because of the fluorescence, but because of advances in the ability to do not just size distribution, but shape distribution. Next chart. So, high-level mission concept. We've got the phasing orbits that I described earlier, targeting the Venus injection, standard Hohmann transfer, and correction maneuvers to target the entry interface coming up on Venus. And the mission design has been enforcing, key things like Earth observability. We are looking at how we can do day-night targeting, looking at different latitude targeting, understanding relative velocities of the local winds. And so we've gone through a couple iterations of our mission design, and we're starting to feel like we've got a handle on it. But this is an area that we're, of course, looking for collaboration, since planetary communications and navigation is one of those challenging capabilities you need to be successful. Next chart. And so when we get to Venus, we target an entry interface and release the probe a couple hours before that entry interface. And our plan is to actually do a parasith raise so that we can improve the comm windows, maximize the duration that we can talk to the probe relative to our Earth coverage. And so the link budgets for this and all the trades between, you know, how much do we burn versus what the value is, those trades are all moving forward to manage this communications concept. Next chart. And I should say we're also looking at direct to Earth as a potential backup, and so we're trading that in the space as well. So I think you may have seen charts like this from Raj. You know, we're very thankful to be collaborating with Ames on understanding the entry conditions and TPS sizing. And so, you know, notionally looking at a range of entry flight path angles, and, you know, the mass budget currently has the high heat load case, but, you know, we're looking for opportunities to reduce that and potentially reduce the TPS thickness. Next chart. Of course, this is, you know, what the science is all about. We want to get into the cloud layer. So, you know, how do we do it? Well, before separating, we are planning a level of spin up, and so even though this shape is ostensibly you know, dynamically stable in hypersonic regime, we have a lot of flow regimes to work through, you know, all the way through subsonic. And so we think some gyroscopic stiffness will be useful, and it looks like we have a good mission concept with the Photon spacecraft actually spinning itself up before the release. I mentioned the comms burn and the coast phase before we hit entry interface, and the science, you know, mission begins once we get through the heating pulse. You know, 100 seconds after, you know, we enter the clouds and we start our data collection before leaving the clouds and working to ensure that we get all of our science data back. You know, we're not planning to survive to the surface. You know, we don't have a design requirement to, but if, you know, if we make it, we want to take advantage of everything we can. And so that'll be a pretty interesting experiment to run. Next chart. So yeah, that was just a very high level overview of where we're going with Venus, and you know, we're working hard to get to a you know, preliminary concept review in the next few weeks, actually, and you know, work to establish collaborations, lock down the science instrument, and start managing the long lead items. Aeroshell is a pretty important one, for example, in addition to the instrument. One of the, I guess, things I'll leave with, and I see Pat's had a question about what kind of the status of the build is. So one of the nice things about this is that our capstone mission is investing in the capability of the rocket, which is upgrading the Electron, as well as the high energy Photon with the Hypercurie investment. And then our ongoing development for Escapade is resulting in the operational systems like our X-band communication systems that are required. And so a huge amount of the work required for Venus is actually being done right now on these other programs. And so the focus for our Venus mission is really filling the holes on things like instrumentation and the Aeroshell. So with that, I'll say thank you. Hopefully that was roughly on time, and happy to answer any questions.
It was. Thanks a lot, Richard, and I'm glad that you made it. There's a couple of questions in the chat. The first one of which you already answered with how far into the build of the probe you are. So let's start with Jill Bayer then. Are you planning on rideshare opportunities for interplanetary, or just dedicated missions? And he's also asking for a cost range of the two sizes of the kick stage. Very interesting question as well.
Yeah, absolutely. So, you know, we kind of view both of them as tools in the kit. We really think that dedicated launch of small spacecraft for planetary science is really important tool for principal investigators. We've had a couple meetings with the Planetary Decadal Survey, both Venus and the giant planets panels, to emphasize that point, to try to get the AOs like Simplex 3 to sort of be balanced in their in the playing field, and to provide PIs more tools. So we think dedicated launch is super important, and that's part of the reason for doing this mission, is to really put our money where our mouth is and show that it's impactful. But with our Escapade mission, we're in the thick of a planetary mission that's using rideshare. It has challenges for targeting an escape asymptote off of a rideshare. But luckily, we have some key capabilities like our in-space propulsion systems, which are really well suited to resolving those challenges. And so we want to see more dedicated launches. There aren't enough opportunities for that today, but we think rideshare is also a very useful tool. And so we hope to do missions with both in the future. On the price question, you'll have to reach out to me by email, and we can talk offline. We're always happy to support formulation efforts and provide ROMs and team with folks that are putting proposals together.
Great, thanks a lot for that. One question for myself. So as a privately owned company, so how do you select your instruments? So what are your criteria in terms of scientific value, for instance, or where are your priorities?
Right. So I think there was a real alignment of interests. Pete really set the priority and at a high level of wanting to contribute to astrobiology and the search for life. And so that was sort of the guiding light. But from a scientific perspective, we take our guidance from scientists. And so we're very, pleased to be working with Sarah and her team, really a world-class team who have come together and they were looking more broadly with the Venus Life Finder study that I think Sarah spoke to earlier this year to understand what the potential for these small, medium, and large missions were for advancing astrobiology at Venus. And so they said, well, what Rocket Lab is trying to do is a great example of a small mission. And so they have taken our SWAP constraints and said, with that, what's the best that we can do? And so these are two of the instrument opportunities that have come out. But like I say, we're looking for collaboration. We're looking for partnerships, and so some of those practical programmatic observations will, of course, guide instrument selection.
Thanks a lot. So there is another question from Jill. How do you avoid ablation product contamination of the sampling path? That's probably related to one of the earlier slides that you had.
Yeah,
did you take a look into their passive system called ENIS, or how do you do that?
Yeah, it's a great question. It's something that we've talked a lot about. There's been a lot of hand wringing about. So one approach is to if you want to actually flip back to one of the configuration charts, you'll see we have a TPS plug at the inlet. I think it's forward. I think maybe right there. You can see so the basically 3D woven carbon is surrounding the inlet port at the stagnation point, and so we hope that the simpler material properties from that help minimize it, but really it's going to be a big characterization problem. Which is, which we've looked at to first order. There are some great papers out there that look at the constituent ablation products for materials like pica, and so you can start to get a handle on it that way. One of the nice things about the science objectives are on the TLS side, on the one hand, you've got a very narrow pass band, and so you really only have to look for contamination products in a very narrow wavelength band, and so that can help. For the nephelometer, one approach would be to put a window in the back shell. So, like I said, we picked the TLS to do the preliminary design here, but the nephelometer probably wants a window on the back shell, and the objective there would be to push the focus out into the free stream where you don't have to worry about ablation products, but then you do need to worry about the window contamination. And so, great question. Not all the answers are on the table yet, but it's certainly identified as a key area that needs to be worked.
Great. Thanks a lot, Richard. So there is no further questions in the chat right now. In case that you have any further ones, please do not hesitate to send an email to Richard.
Thank you.
So, all right. With this last presentation of the technical session, we are actually at the end of our technical sessions of this year's IPPW, at least the technical part of it. So I particularly would like to thank all presenters of today for providing the content for another great IPPW session and for all follow-up discussions that we had in the chat. I also would like to thank again my co-hosts, Pat, Ashley, and Jim, who did put the program of today together. Before we conclude, and in good old IPPW tradition, we do have a few announcements and news we would like to share. The new program organizing committee is just about to pick up duty. Our new team is going to be Jill Bayer, who continues for another year, Alina Probst, Manuel Dominguez Pumar, and Jacob Israelowitz. Thanks a lot for volunteering. Jacob will give us, before we go to the log, a quick update on a JSR special edition. Jacob, are you on the line?
Sure, I can speak to this now.
Yes, please do.
All right, so I'd like to take a brief moment to remind our audience of an experiment from last IPPW. Some of our 2020 abstracts were turned into full-length papers and put into a virtual collection for AAA Journal of Spacecraft and Rockets. A number of these papers are now online. The link is there below. A few more are still in review. The full collection will likely be published by end of calendar year, and we'll go ahead and announce it to the IPPW email list once it's complete. I'd like to give another big thanks to Carl Edquist of NASA Langley for being the associate editor in charge of this virtual collection. And with that, I'll hand it back to you, Robert.
Thanks a lot, Jacob. So besides the program side of things, also the work of the local organization started, and David Cornelius agreed to give us a preview on what is planned for next year on behalf of the LOC. David, I've seen your face already. There you are. Okay, please take it away.
Yeah, hopefully you can all hear me, Robert. Thank
Yes,
you very much.
we do.
Yeah, we wanted to give a preview, maybe try to close out the virtual session for 2021 with a message of hope. We didn't prepare a video as impressive as the Olympic closing ceremonies here, but maybe it's just as inspirational. If you can go to the next slide, please. As many of you are aware, we originally planned IPPW 2020 to be in person in Monterey, California. Because of COVID in March of 2020, we had to go to a virtual solution here, which we're still living through and still doing 2 years in. Despite the large uncertainty about how things are evolving, they've been on a positive trend. We've been talking to the IOC, and the local LOC has decided that we should go ahead and proceed with a presumption that we might be able to have, or we will be able to have a on-site, in-person, what we'll consider as normal as you can, IPPW for 2022 back in Monterey, California. So we've started the planning process with that presumption to address things we need to do, like long lead items like lodging and venue options in Monterey, California, which is a pretty popular destination in summertime. Obviously, we'll keep an eye on the evolving situation with COVID, and we'll have to adjust accordingly, including potentially having to revert to a partial or full virtual conference again based upon what's happening. But we're hopeful that all our domestic and international colleagues will be able to travel and visit us in Monterey in 2022. Go to the next slide, please. We've picked out this week here, June 11th and 12th for the short course, and then the 13th through 17th for the workshop itself. Try to dodge all the other activities going on here that we've put in this calendar. You can see, including holidays, federal holidays in the U.S. and other conferences. There is an overlap with this with a planned Mars atmospheric modeling and observation group in Paris, France. This conflict actually existed in 2020 when we had picked a week, and through discussions with the IOC, there was a lot of interest in getting IPPW back into the June timeframe, which was kind of the normal IPPW meeting window. So this is the week we're planning for in terms of logistics and trying to plan on-site activities. Let's go to the next slide. This slide summarizes our LOC, our organizing committee. Myself, I'm David Cornelius. I'm the program manager for our on-site engineering and services work we do at NASA Ames Research Center in Entry Systems Technology. Aga, who is the Deputy Director of the Exploration Technology Director at NASA Ames, will be co-chair, as she was in 2020. Our support team includes Sharon McKee, who is the Assistant Division Chief Operations for the Entry Systems and Technology Division at Ames, which is one of our primary customers on our contract work too. And then Valerie Escobar, who is my business ops manager and a wild talent with regard to organizing things. We also have, as we always do, a lot of participation from our NASA colleagues in terms of planning and support. Helen Wong at NASA is going to help. Debbie Osterland, Wilson Kai from AmeriCorps, Raj, as you all know, will be a part of our LOC, and then Todd White from NASA Ames. And thanks to all our LOC partners here in terms of helping with planning and logistics. Let's jump to the next slide. Wanted to put a couple of slides in here about NASA Ames to refresh people's memory. We are obviously, the work we're doing is closely aligned with Ames, and Monterey is not that far away. So we have a couple informational slides. One is a historical picture here of Ames back when it started up in 80 years ago. I'll just leave it there for you guys to review later. We'll skip to the next slide. Also wanted to include the some of the core competencies of NASA Ames: air traffic management, entry systems, which is near and dear to our heart, advanced computing and IT, intelligent and adaptive systems, low-cost space missions, aerosciences, astrobiology and life sciences, and space and earth sciences. Let's jump to the next slide. And to highlight, we also wanted to highlight some of the facilities at Ames that are world-class, including their wind tunnels, the ArcJet complex, obviously, as NASA's primary ArcJet complex, the range complex for ballistic range testing and other testing, on-site simulators, and then obviously advanced supercomputing capabilities that are located at Ames. Let's go to the next slide. The rest of these slides are really, our hope is preliminary logistics and try to get everyone excited about thinking about maybe coming to Monterey and visiting us in 2022. This is historical locations for IPPW, and with some of the California locations highlighted, including the ones that have happened down in Pasadena, and then obviously in the Mountain View area near NASA Ames and in San Jose in the past with our 2020 and 2021 virtual conferences listed. Let's go to the next slide. And then just a few slides on logistics. So obviously there's we have multiple international airports. Hopefully we'll be able to fly into these, and there's great transportation options to get to Monterey from these airports, which we'll include more detail on in the future. So go ahead and jump to the next slide. And the next couple are really just to identify and get you thinking about your tourism planning part of your trip here out to California. Some historical items from Monterey itself in terms of some of the attractions, including the aquarium and Cannery Row. And then the next two slides, if you go to the next slide, is we have identified and some of the attractions and points north, 1 to 2 hours north, some of the famous attractions, including the Winchester Mystery House and Muir Woods, and obviously San Francisco attractions, Lick Observatory, one of my personal favorite places to go on the planet. And then the next slide is a reminder of some of the attractions 1 to 2 hours south of us here. So to jump to I believe it's the last slide here, which was just to say that we are, hopeful and looking forward to seeing everyone in person in 2022 in Monterey. Anyone who is interested in discussing sponsorship, please reach out to myself or Valerie, and we'll be happy to accommodate you and have that discussion. But we will update the IOC and the IPPW community as things evolve, but wanted you to know this and to keep an eye on it and maybe block your calendar out for us so that we can hopefully all be together again after 2 years of virtual meetings next year in Monterey, California. Thanks very much.
Thanks a lot, Dave, for the appetizer, and I'm sure we will all block our schedule right now. I think with this great outlook and our hopes for meeting again physically next year, we are just as close to the Olympic Games closure ceremony as we can probably get. So the last two IPPWs came with quite some challenges, in particular in terms of keeping contact and continuing the collaboration within the IPPW community, and this vision is really great. So despite the issues that we had, still our program organizing committee, Som Tuta, Jill Baye, Björn Halbert, and Todd White managed to put a set of virtual workshops together, which enabled an excellent exchange and great discussions. Also the support of AMA, who were hosting the website and did organize the announcement, and JPL, in particular our web host Tim, who provided the virtual meeting support, was awesome. So well done POC and operating team. Well done also future LOC. Thanks a lot for this. Let's give the team a big random virtual applause to thank them for the great work. We're almost done with our session today. And with this, and together with my co-chair, Ashley Corson, who is already in her well-deserved holidays this week, I would like to close this year's IPPW on behalf of the International Organizing Committee. We wish you all the best and can't wait seeing you next year in Monterey. Take care and stay safe wherever you are. And I wish you all the best for the next weeks until we start again with the organization of next year's IPPW in Monterey.